Welcome to the dissociation curve and transport calculation. So hopefully that you've already read through this a little bit in your book, as well as seen some of the resources that I've put in Blackboard for you as well. So make sure you go over those. Even that little video that I put in Blackboard might be helpful to you, as he sort of explains it in a different way than I do, as well as a different way than the book puts it. But as many different ways I like to try to give you, because that will help you understand it better in different ways. So that way, if one way sticks and you understand it that way, perfect, right? My goal is to help you sort of understand the concept of the oxygen dissociation curve, as well as how oxygen gets used and transported to your muscles, and then how CO2 gets transported from your muscles back to your lungs so you can get rid of it. So this is going to sort of be a little bit of a take it slow, one step at a time, take breaks, make sure you write bullet points as you see them, make sure you're taking good notes, and just go through it slowly. Don't let the material overwhelm you. This information can be very heavy for some people. So just make sure you take it slow, one step at a time, make sure you understand one concept at a time, and then we'll move from there. So the first thing I want to talk about is the content equations. So we went over the three content equations last time. So the three content equations were the CCO2, which is the pulmonary capillary content, right? So the content of oxygen in the pulmonary capillaries. There was the CaO2, which is the content of arterial oxygen. So after we go through the pulmonary capillaries, and then we have our tissues, and then coming back to the lungs. And usually it's supposed to be in the pulmonary artery, but as close as you can get to the lungs as possible. So most likely nowadays a central line. There's the CVO2. So the CVO2, the CCO2, and the CaO2. These are three different equations, even though they both calculate the content of oxygen. So remember, the CCO2 is hemoglobin times 1.34 and then we're going, there's no saturation in this one because you don't stab people in the lungs. You're going to add that to what's in their plasma, which in this would be the P big AO2. So you have to calculate alveolar oxygen times 0.003. So it's that big long one where you have to multiply it by a very, very small number, and that's okay. But the big thing here is to remember, with capillary content, with pulmonary capillary content, you have to calculate your alveolar air. And I see that equation, that part of the equation mixed up quite frequently here and there. So hemoglobin times 1.34, then you add that to the PaO2, P big AO2, right, times 0.003. So you add what's on the hemoglobin in the lung, and then what's in the plasma in the lung, and that gives you capillary content. So this is a way, and this sort of gives you the big picture of this. Why am I looking at these three things, Derek? Well, if we're looking, I'll just write an L up here for lung, and then the T is for tissue down here. And you could pretend this is like a leg muscle for tissue down here. So when we're looking at this, capillary content represents how easy it is for gas to get into the pulmonary capillaries, right? It's this relationship right here. If this is low, and what's a normal? So I recommend writing these out and writing normals. A normal CCO2 is 20 volumes percent. So when we're looking at this, if the CCO2 is low, if it's decreased, that could be due to a diffusion issue. It could be due to a perfusion issue. It could be due to anemia. It could be due to hypoxia. In other words, let's say this patient is at high altitudes, Or let's say this patient is somehow oxygen deprived, or diffusion defect, like there could be a pulmonary disease going on, like an ARDS or pulmonary fibrosis or pneumonia. All those diffusion defect diseases could cause a low CCO2. Same thing with a decreased perfusion could cause a low CCO2 as well, right? Even if a patient is anemic, which means very low red blood cells, that could cause a low CCO2. So if you're doing these three equations and you start off with the CCO2, be like, okay, how healthy is this first relationship, right? And that relationship is poor, that's most likely where your problem is. So then I would focus on what their red blood cell count is, right? We would do a CBC, look at the red blood cell count. Or we could look at their diffusion, right? We could look at their A to A gradient or PF ratio. We can look at a DLCO if they're a spontaneous patient. We can look at their X-ray to see if there's any issues going on with their lung disease. We can look at their blood pressure and heart rate to see if their blood flow is decreased. That's causing a low CCO2. So that's the first one we would look at, right? So if we're trying to figure out what's wrong with a patient, and I want to look at the CCO2 first, that tells me if there's any diffusion or perfusion issues. If that is fine, let's say it's 20 volumes percent, which is normal. Then I'm going to look at my CaO2. So this one tells me my diffusion's good. My CO2, my normal value is 20 volumes percent as well. And then the equation's a little bit different. So I have my hemoglobin times 1.34 times my saturation. Remember, and the saturation needs to be in a decimal form. So if they're 97% saturated, you would put 0.97. And then we're going to add that, because that's what's on the hemoglobin, to what's in the plasma. So the plasma is going to be my P little AO2 in this situation times 0.003. Because remember, the plasma does not carry, it does not have the ability to carry 0.003. There we go. The plasma does not have the ability to carry as much oxygen, and that's why we have to multiply it by 0.003. That's how much milliliters are carried per millimeter of mercury, right, per pressure in the plasma. So we add both of those up, and a normal should be 20 volumes percent. Okay, so let's say we do have a normal CaO2. Okay, so that means we're delivering a good amount of oxygen as far as content goes to our tissues. This is great, good news. All right, so as our tissues consume oxygen, they produce CO2, which then goes back up. And now I want to see how much oxygen, content of venous oxygen, is left over. So by looking at CVO2, I'm actually looking at how efficient my metabolic rate was. Okay, so a CVO2, a normal CVO2 is 15 volumes percent. Okay, so I got my CCO2, my CaO2, and my CVO2. I got my normals. Okay, now what's my calculation for CVO2? Well, my calculation for CVO2, not too much different. I have my hemoglobin times 1.34 times my SVO2, my venous saturation. Remember, that's a decimal form, just like the CaO2. And then I'm going to add it to what's in my plasma, which is my PVO2, pressure of venous oxygen, times 0.003, right? So hopefully it's the same equation but as the CO2, but we're just plugging in venous values, PVO2 and SVO2. So once you plug these in, you're going to get how much content of venous oxygen there is. So 15 volumes percent is normal. So the normal gradient between the two, the normal consumption of oxygen by the tissues, is going to be 5 volumes percent, right? Because a normal CO2 is 20 volumes percent. A normal CVO2 is 15 volumes percent. So the difference between the two is 5 volumes percent. In other words, the tissues use roughly 5 volumes percent of oxygen, of content of oxygen. And that's a normal metabolic rate. And so this is good. So when we have tissues that use 5 volumes percent or more, it becomes deoxygenated. In other words, not all the oxygen comes out, but it pulls it enough to cause cyanosis or to cause deoxygenation. Not necessarily cyanosis, but it deoxygenates the content significantly. So when we take it back to the lungs, it's a lot lower than where we got it. So let me ask you this. If someone's CaO2 was 20 volumes percent, but now their CVO2 is only 3 volumes percent, okay? What happened? What area is causing the significant oxygen reduction in your patient? Well, the area that had the significant reduction wasn't the lungs. Your CCO2 was fine, your CaO2 was fine, and then their tissues consumed an excessive amount here. So instead of consuming only 5 volumes percent of oxygen, they consumed 15 volumes percent of oxygen. So that means our tissues are highly metabolic. They're consuming a high amount of oxygen. This happens when you're running a temperature, right? When you're acidic, right? When your body is producing an acid in a high metabolic rate. So this could happen in a situation like a sepsis, where you have a blood infection and your whole body is running through a massive high metabolic rate. So you can actually see this in patients. So if I were to look at a patient and be like, why are their oxygen levels so low in their body? Then I can actually look at my CCO2, my CaO2, my CVO2 to help point out where the problem is. So in this situation, in the example that I gave you, where the CVO2 was extremely low and the other ones were fine, then that tells me that there might be an infection going on, and we should grab a blood sample, culture it, right? We should look for signs of infection and possibly start broad spectrum antibiotics until we find the culprit for the infection. Right? I hope that makes sense to you, but these will be useful in critical care medicine as we start to look at what's causing my patient to have these low oxygen levels. Because remember, we need to sort of find out, like a detective, what's going wrong and where, right? In the meantime, we're going to give them lots of oxygen, right? We're going to be therapeutic. We're going to give them as much oxygen and ventilation as they need. However, it's still good to figure out where is our problem, and let's work the problem instead of just grasping randomly at therapies and hoping one of them works. When you're doing this, when you're looking at the CCO2, you're ruling out the lungs. If it's normal, you ruled out the diffusion issue. If their CBC shows a normal red blood cell count, we've ruled out a anemia issue. If we have a narrow A to A gradient, in other words, a very tiny A to A gradient, then we've ruled out a diffusion issue, right? If we ruled out blood pressure issue, if their blood pressure is within normal limits for them. So that rules out with CCO2 an issue with the lungs. CaO2, that would also be low if we had a low CCO2. So that's one of the things that we'd see there. Now, or if we had dysfunctional hemoglobin, CCO2 and CaO2 would both be low as well. So when we're looking at this can help us sort of determine if we have a lung problem, anemia problem, blood pressure problem. If those aren't the problem, then we might want to look at the tissue. So that's why looking at the CVO2 and the CCO2, CaO2, all three of those together can give us an indication if our patient does have a metabolic issue, like a massive high metabolic rate, like an infection, or do we have a lung problem like a viral pneumonia, right? So this is going to become very valuable as we get into, hopefully, critical care medicine, looking at how the body responds to all these different situations. So this next part, we'll be talking about the oxygen dissociation curve, and this is a sigmoid shaped curve, and there is a good video that I put in Blackboard for you, so hopefully you'll take some time to pause this, go look at that if you haven't already, but I'll give a quick overview of this, and this is something that can get lost on some people, and it's something that you just need to spend a little bit of time with, but it's understanding that your body needs both a pressure of oxygen, right, or PaO2, so we need that pressure of oxygen in our plasma, as well as saturation, as well as oxygen being carried on the hemoglobin molecule. Both of them are extremely important. And so this looks at the cascade of things. And so we're pretty much looking at hemoglobin here. And remember, hemoglobin is a big factor in being able to carry oxygen. That's why if a person's anemic, one of the first things that we'll see is their oxygen levels are going to be low and they'll go into multi-organ system failure if they're anemic eventually, because they can't carry as much oxygen. Their content of oxygen in their bloodstream is going to be very, very poor. So we need both pressure, we need hemoglobin, and we need saturation on that hemoglobin in order to get adequate oxygen delivery to our tissues. So when we're looking at the oxyhemoglobin dissociation curve, this is looking at how oxygen binds to the hemoglobin molecule and that relationship. So get ready to talk about relationship. So this is an S-shaped curve. So here I'm going to draw a little axis here. So on your x-axis, you're going to have your PO2, your pressure of oxygen. We'll just pretend we're talking arterial here. So P little AO2. On your vertical saturation, we're going to be talking about your y-axis. We're going to be talking about saturation, right? So as we're looking at this, we need both pressure and saturation. So this relationship between pressure of oxygen and saturation as it relates to the hemoglobin is not linear. It is not a straightforward, predictable relationship. It is actually what's called S-shaped or sigmoid shaped. So we're going to start low, and as hemoglobin starts to change form, so as oxygen starts to bind to hemoglobin, hemoglobin says, oh wait, what is this? I really needed this, and so more sites on the hemoglobin molecule open up. The hemoglobin molecule actually changes shape. I kid you not. So the hemoglobin molecule actually changes shape once oxygen starts to bind to it to collect even more oxygen. So that's what makes this curve sigmoid shaped and not linear. So as oxygen starts to bind, it's going to change the shape, and then eventually we're going to hit a point of diminishing returns. Okay, so when we're looking at this, the higher the PaO2, the higher the saturation. Yes, and then we have the point where we actually reach what's called a safety zone, or a plateau, if you will. So when we're looking at this, we have a situation here. We're at a pressure of 60 millimeters of mercury, and I'll just put T here for torr, but 60 millimeters of mercury. I should have a saturation of roughly 90%. So that means that I have a safety net. As long as I keep my patient's pressure of oxygen above 60, the saturation on the hemoglobin molecule should be 90% or above. In other words, once their PO2 is above 60, I should have a good safety net. I should be able to carry a lot of oxygen, because remember, higher saturation, the more oxygen we're carrying to the tissues. The lower the saturation, the less oxygen we're carrying to the tissues, and that's not healthy for the tissues, right? That's literally starving or choking the tissues, and that's where they start to go in anaerobic metabolism and create lactic acid, which then changes your pH, and obviously life forms usually don't survive in very acidic environments as far as human life forms go, right? So this is very important that we try to keep their saturations and their PO2 both together, because seeing that their PO2 is 60 and their saturation is 90 or above, that tells us that we're able to send or carry a lot of oxygen to our tissues. That keeps our life functions going. Those tissues include your brain, your heart, your kidneys, your liver, so on and so forth. Those very important organs you are currently relying on. So 60 and 90 is a critical value as we're looking at this. So when we reach up here, we're not going to have a big change. If I were to go to a PO2 of 70 or a PO2 of 80 or a PO2 of 130, right? We're not going to have a very high change. Hopefully you guys can all see this. We're not going to have a very big change in our saturation. We're in sort of a safe zone. Our saturation may change from 90 to 93 or from 90 to 98, right? So on and so forth. But we're not going to have a big change for PO2s above 60, right? So that's sort of that safety, that flat zone that's up there. Well, what happens? And why is this important? Because if we have a PaO2 less than 60, so you have a patient, they're hypoxic in front of you, you can see that they're turning that grayish purplish color, right? And you draw an arterial blood gas while someone's putting on oxygen on this patient, so on and so forth, and you draw a blood gas and you see that their PaO2, let's say it's 50, or let's say it's 40. So we see that as a PO2 goes below 60, there's a dramatic decrease in their saturation. So once we go less than a PO2 of 60, there's a dramatic decrease in their saturation. This is what we call the danger zone, or I don't know, I just like the term danger zone. So there's a dramatic drop in the ability to carry oxygen with a PaO2 of less than 60 millimeters of mercury, right? I'll repeat that again. There's a dramatic decrease in the ability to carry oxygen with a PaO2 less than 60 millimeters of mercury. So that means we have dramatic decreases in our saturation. So if we go from a PO2 of 60 to a PO2 of 50, we're going to have a dramatic drop. So in this case, a PO2 of 50 would actually lead to a saturation of 70%. Sorry, 80%. So when we're looking at this, that's going to change significantly how much we're looking at carrying oxygen, right? If we go down just 10 millimeters of mercury, just 10 millimeters of mercury less than 60, we're going to have a dramatic decrease in our saturation levels, a dramatic decrease in the ability to carry oxygen to your tissues. However, if we go from 60 to 70 millimeters of mercury, if we're going the other direction above 60, then our saturations may only change by about 3 to 4% at most, right? Because that's in our safety zone, right? So as we get lower than 60, we're going to have that dramatic drop in saturation. If our PaO2 was 40, then our saturation would be 70 at this point, 70% saturated. So that's a huge drop for just 10 millimeters of mercury. So this is showing that once your patient has a PO2 that's low, their saturation, their ability to carry oxygen is going to be decreased, because what happens here, and we'll go back to what I started talking about, the hemoglobin, once it starts carrying oxygen, it changes shape to allow for more oxygen sites to open up, and that's where we get that good flat safety zone at the top here. But when we have oxygen that starts to pull away from the hemoglobin molecule, then we are going to have a dramatic decrease in the ability to carry oxygen, right? So that's why it's important to keep your patient's PaO2 levels above 60. All right, and even in some critical care medicine out there, as of recording this lecture, a lot of our goals for critical care medicine is to keep someone's PaO2 55 and above, right? To keep it sort of in that higher range. So that's a saturation of around 85 and above. So that means we can still carry some oxygen to the tissues, and that's hopefully helping their lungs if we're not over ventilating and letting their lungs sort of repair itself. And that goes into that whole permissive hypercapnia thing I talked about with the last video. So this is the oxyhemoglobin dissociation curve. You're like, okay, this is the normal relationship. So how do I know that I have sort of the normal relationship going on? Well, one of the things that we like to look at if your patient has a normal curve, a normal relationship. So we sort of want this, and we want to keep our patient in this safety zone up here as much as we can. But there are situations that the body creates or that we might create that can cause this relationship to shift. In other words, there are situations where I can get very low saturations for high pressure. In other words, this danger zone might move this direction. In other words, I have a higher pressure, let's say a pressure of 70. If I have a pressure of 70 and my saturation is only 80, that means my danger zone moved over. That means I'm not carrying a lot of oxygen even though I have a lot of pressure, right? And that's called a right shift of the curve. That means I'm carrying a lot of oxygen in my plasma, but hardly anything's being attached to the hemoglobin molecule. Oh, that's not good, right? Because that means we're not carrying a lot of oxygen. Well, if there's another situation where we can have our safety zone up here actually shift this way. In other words, for a lower saturation, let's say someone's PaO2 is 50, right? But in this situation, in a left shift situation, even though their PaO2 is 50, their saturation could be in the 90s. So that's called a left shift, right? You have your safety zone shifting to the left. In other words, for a lower pressure, I have a higher saturation. So a left shift is a lower pressure for a higher saturation. So if we're looking at this, so we're looking at a left shift and then a right shift. So left shift equals low pressure, high saturation. And a right shift is high pressure for a low saturation. Okay. So what causes these things to change? What causes this curve to change? Well, one of them is just your body normally. And the video also goes over this. In the lungs, you have a low temperature, you have a low metabolic rate, you have a low pH, you have high pH but low hydrogen ions, right? Because you're not acidic in your lungs, right? That's where you're getting rid of CO2. You're getting rid of carbonic acid. So as far as the lungs go, your lungs have a low hydrogen ion. So I'm writing a hydrogen ion, which actually means a higher pH or an alkalotic pH. But you'll see why I'm doing hydrogen ions here, okay? So just stick with me. In your lungs, if you have low hydrogen ions, okay, low H pluses, you also have a lower temperature, and you have low metabolic rate, which will do 2-3 BPG. So that's a product of, that's part of like the glycolysis issue, so that's your metabolic rate or metabolism. So in your lungs, you don't have all this going on. Your lungs do have muscle, but compared to your leg muscle, right, do they have as much metabolism going on? No, right? They're not consuming oxygen. They're actually doing the opposite. There's less metabolic tissue going on in your lungs than there is in your leg muscle, for instance. So your 2-3 BPG, your glycolysis part of it, is going to be lower. Your temperature, because temperature is part of the byproduct of metabolism, right? So if I were to decrease some metabolism significantly, I could in theory decrease their temperature, right? Because that's their body with ATP and everything. So in your lungs, they're getting rid of CO2, so that's why your pH, you have low hydrogen ions, right? So anything that decreases hydrogen ions, that causes your body to go into alkalosis. Anything that decreases temperature, like hypothermia, or anything that decreases metabolic rate, let's just say like paralytics, right? If we give a patient chemical paralytics, all those will cause a left shift of the oxyhemoglobin dissociation curve. So in other words, if I have a patient that's hypothermic, they're going to have a high saturation for a low pressure. Okay, so any of those things can cause this curve to be abnormal, okay? They can have a high saturation for a lower pressure. Other things that can cause a left shift would be carbon monoxide poisoning, and also fetal hemoglobin. Fetal hemoglobin, we already talked about fetal hemoglobin in the red blood cell PowerPoint as well, where it's purposeful to carry more oxygen on lower pressures. Well, there you go. You just learned in that previous lecture the beginnings of the oxyhemoglobin dissociation curve. You learned that little babies in utero, so when you were in utero, you were left shifted on your curve. You were able to carry and have high saturations for a very low pressure. That means you didn't have to steal all of mom's oxygen in her plasma, just some of it, and you were very efficient with it, right? So all those things can cause a left shift. When we're looking at a right shift, it's going to be the opposite, right? In the right shift, we have a high pressure for a low saturation. So when we're looking at the right shift, we're seeing things that would cause an increase in hydrogen ions. So this would be an acidosis, right? Hydrogen ions, acidosis. I was trying to write acid there, but it's not going to do it for me. Use your imagination. High hydrogen ions. So this is going to be highly metabolic tissue if your patient has a very low pH, because remember, pH is a negative logarithmic scale, and so that's why if you have high hydrogen ions, it's actually a low pH because it's a negative logarithmic scale. Don't worry about remembering that yet, but high hydrogen ions means high acidic level, right? Their pH is low. What if they have an increase in temperature? Hyperthermia. Like they're running a fever, a massive fever, because they have a massive infection going on. So that can cause a right shift where their saturations will be low, and we can get their PO2s to 120, right? We can increase their P little AO2 as much as we want to, but because they're right shifted, they're not going to have much change in their saturation. Okay, and then the other thing would be here, hopefully you see a pattern developing, an increase in 2 to 3 DPG or BPG, biphosphoglycerate or diphosphoglycerate, depending on the source you read. They're both the same thing. They're looking at glycolysis. They're looking at metabolism. So if I have a patient that's running a massive temperature, right, and a high metabolism, and they're creating a bunch of acid because they're anaerobic, they're more likely to be right shifted on their curve. Well, what does right shifted mean to you? If a person is right shifted, what will be the ability for their body to carry oxygen to their tissues? Well, it'll be decreased, right? Because most of the oxygen that's carried to your tissues is carried on your hemoglobin. So no matter how much pressure we increase their PO2, their ability to carry oxygen to their tissues is poor. So they're going to have tissue hypoxia, right? And so they're going to, even though their blood is going to have low oxygen levels, so is their tissues. And then it's going to make their acidosis worse, right? We're going to have even more issues. We're creating CO2 and going into the Krebs cycle and all that bad stuff, right? So if a patient's right shifted severely, then we're going to have a decreased ability to get oxygen into our tissues. Well, what about a left shift? That sounds great, right? And it's good if you're a baby. But other than that, you have a high saturation for a low pressure. Well, here's the thing. When we get to the pressure, if you're left shifted and you have high saturation and low pressure, remember at the tissue level, you need to be able to drop off oxygen to your tissues. Well, who starts the oxygen coming out of the blood and going into the tissues? It's not the oxygen that's on the hemoglobin molecule, it's actually the oxygen that's hanging around in the plasma. In other words, if you have a low pressure gradient between your tissue, so I'll just put this tissue and then I'll draw a red for blood. Right, if your pressure gradient is low, right, and remember, P little AO2 is how much is in the plasma. If there's hardly any PaO2, do you have a lot of need? Do you have a lot of pressure gradient to really pull oxygen over? Let's say they're almost even. Let's say the PaO2 is only 40 millimeters of mercury, and the pressure of oxygen that's already in that leg muscle is 40. There's no pressure gradient there, and we're not going to pull any oxygen from the bloodstream. So in order to get the oxygen off of the hemoglobin molecule, we first need to pull the oxygen starting from the plasma. Now we're not going to rob all of the oxygen in the plasma, just some of the oxygen in the plasma. So in order to get oxygen off of the hemoglobin molecule, once we get to the tissues, our PaO2 needs to have a high pressure gradient. If that pressure gradient is not high, then we're not going to start that cascade. In other words, if our PaO2 is low, that hemoglobin molecule just continues to hug and hold on to that oxygen molecule, and it will pass by the tissues. In other words, we're still going to rob the tissues of oxygen. So whether a patient is right shifted or left shifted, their tissues are not getting adequate oxygen. I'll repeat that again. Whether a patient's right shifted or left shifted, their tissues are not going to get adequate oxygen. So you're like, Derek, what do I do about this? Well, therapeutically, if you know your patient shifted, you draw blood gas and they have a low pressure for high saturation. Okay, they're left shifted. Okay, what do I do in the meantime until I figure out what caused it? Hey, give them lots of oxygen. If they're right shifted, right, you see that they have a high PO2. Let's say their PO2 is 120, but their saturation is 70. Okay, so what do I do in the meantime, Derek? Hey, give them as much FiO2 and pressure as you can until we figure it out. So when you're looking at this, hey, you just drew a blood gas and you see that their PaO2 is 40 and their saturation is 98%. Oh, great. So they're left shifted. What could cause this? Well, if you drew that blood gas, then you would know what their pH is. You would know what their hydrogen ion concentration is, right? If their pH is super low, like they're hyperventilating, then that's something that you can work on, like a neuro injury, or if that's something that you can work on where we can intubate, we can sedate, we can do things to help with that. There's even medicine we can give to decrease someone's alkalosis. Right? Maybe they're hypothermic, right? Maybe they were found down outside during a frozen winter day, right, in a park or something, and they have a low temperature. We'll start warming them up and their curve will start acting more normal. Let's say they were high metabolic, let's say they had a very low metabolism. That could be something that we can fix as well with some medicines to boost their metabolism. What about carbon monoxide poisoning? Was this person in a house fire? Was this person exposed in a garage or a different place where they could have where they could have had carbon monoxide poisoning that's causing this issue? So in the meantime, if a person is shifted, we're going to give them oxygen, whether they're left shifted or right shifted. But then we can sort of work the causes of what's going on. With carbon monoxide poisoning, if you send the blood gas for co-oximetry, and we talked about that in the red blood cell PowerPoint, if you send that blood gas for co-oximetry, it looks at the different types of hemoglobin. So you have it even gives you adult hemoglobin, it gives you methemoglobin, and it gives you carboxyhemoglobin. Carboxy is the carbon monoxide one, and if that's high, then you know that it's probably carbon monoxide poisoning, and then we would work to treat the carbon monoxide poisoning before their organs go into failure because there's lack of oxygen being delivered. So whether you're left shifted or right shifted, you're not delivering oxygen to your tissues. You're hypoxemic and hypoxic. Right? So hypoxemic means low oxygen levels in the blood. Hypoxic means low oxygen levels in the tissues. Right? So hopefully you remember the difference between hypoxemia and hypoxic, right? When we're looking at this. So you're like, Derek, how do I know if someone's shifted? So there's two ways to know if someone's shifted. And your book gives you two ways, and one of them is looking at the curve, and they say, okay, So we'll just section that off over there, the curve. And they say, hey, if a patient's PaO2 is 27, their saturation for a human should be 50%. So this is what's called the P50. So it's looking at the pressure. So P50 is the pressure at which your saturation is at 50%. So if we were to, in theory, draw a blood gas, a blood sample from an artery on a patient, and see that their P(AO2) is 27, but their saturation is 40, or let's say let's do it this way. So we draw a blood gas on a patient, and we see that their pressure is 35, and their saturation is only 50. Which way did we move on the curve? Did we move to the right or to the left? We moved to the right, correct? Right? So we moved to the right. So that means on a higher pressure, we have a lower saturation, which is the definition of a right shift on the curve. Now let's say we do a blood gas and we have a patient who lives up in the high mountains, and they lead climbing expeditions all day long, and then their PaO2 at 50% is only at 18 millimeters of mercury. So that moved to the left. So this patient, if their PaO2 is only 18 and their saturation is 50%, they are left shifted. So that's the P50. Clinically, you're not going to be using that much. You should know that the pressure, a normal level of P50 is 27 millimeters of mercury. Okay, so what do I do clinically, Derek? What does this mean clinically? How do I know if someone's shifted clinically? Because if someone's PaO2 is 27, they're probably going to be very hypoxemic and near death. So what do I do clinically? Well, clinically, there's something called the 4, 5, 6, 7, 8, 9 rule. So 4, 5, 6, 7, 8, 9. So this one is going to be very helpful to you. It is helpful to me. PaO2 and saturation. So this means if someone's PaO2 is in the 40s, their saturations, if they have a normal curve, should be somewhere in the 70s. That means if someone's PaO2 is in the 50s, if they have a normal oxyhemoglobin curve relationship, their saturation should be in the 80s. This means if a patient's PaO2 is in the 60s and they have a normal curve, their saturation should be somewhere in the 90s. Okay, so this tells me I have a normal curve. So here's the situation. I have a patient, they're not doing well. They asked me to draw an arterial blood sample, so I do so, and I see that their PaO2 is 55 and their saturation is 85. Are they shifted on the curve? Is this a normal relationship or an abnormal relationship? And you look at this, hey, 4, 5, 6, 7, 8, 9, if their PaO2 is in the 50s, saturation should be in the 80s, they have a normal curve relationship. So does that mean that we have to go up here and start looking for carbon monoxide poisoning or an infection or anything like that? No, they have a normal curve relationship. Now, here's a different scenario. You go draw a blood gas on a patient that's not doing well, right? Same blood sample from the artery, and you see that their saturation is only 73% and their PaO2 is in the 80s. That's a high PaO2 for a very low saturation. That's a high pressure for a low saturation. What could cause that? Well, then we're looking at, okay, this patient has a low saturation, so their tissues are getting low amounts of oxygen because they're shifted. I need to restore that relationship. So in the meantime, I'm going to give them as much oxygen as I can until I figure out the problem. So I know this is a right shift because it's high pressure for low saturation. So what's their pH level? Is it very acidic? Is there something I can do to buffer it, like giving them a dose of bicarb? Or are they hyperthermic? Should we start to decrease their core temperature? Are they hypermetabolic? Is there an infection that we should start to treat for their body, right? That 2 to 3 BPG, DPG. So when we're looking at this can help you see why your patient's in multi-organ system failure. Your patient can be multi-organ system failure with a good saturation and low pressure because there's no ability to get oxygen to the tissue. Your patient could be in multi-organ system failure because there's a good PaO2 and their saturation's low, because there's no the carrying capacity of the hemoglobin is very, very low, and we're not delivering as much oxygen as we need for our tissues. So if your patient's in multi-organ system failure, one of the things I would encourage you to do is look at the 4, 5, 6, 7, 8, 9 rule. See if they have a normal relationship, right? For PO2 anywhere 60 and above, they should have a saturation of 90 and above, right? PO2 of 50 in the 50s, the saturation should be in the 80s. If that relationship's not there, right? Like my example was, or another example would be, hey, their saturation's 98% and their PO2 is only 40. Well, that's not a normal curve, and that's a left shift because I have high saturations for low pressures. Could they be a carbon monoxide poisoning, right? Could it be a severe alkalosis from head trauma that they're hyperventilating, right? Could there be something like that going on? And I need to restore a normal relationship in order for their tissues to get adequate oxygen levels. So many times these patients that don't have a normal curve where their PO2 to saturation level, that 4, 5, 6, 7, 8, 9 rule, many times they will have altered mental status. Many times they'll have a decreased urine output. Many times they'll have a high liver function test, right? Liver function enzymes. So because they're going into organ failure. And this is where you come into play and you use your expertise and be like, hey, what am I looking at here? If they have a normal curve, then it's not one of these that's causing it, and so I can just increase my oxygen either way. But if it's abnormal, we need to figure out what's causing them to shift on that curve. So I know that's a lot of stuff, but you have the ability to go back and rewind and replay. So let's move on. All right, so this is sort of covering what we did last time, the arterial content. So remember, we can carry oxygen two ways. Oxygen that's dissolved in the plasma still exerts a pressure, and oxygen that's bound to hemoglobin. So when we're looking at this, the more oxygen that's bound to hemoglobin means we have more binding sites, and it keeps on increasing and increasing. That's why it's an S-shaped curve, right? That's why, hey, we have a cascade effect. Hey, you're getting oxygen, well, I'm getting oxygen too. Then the hemoglobin next to it is like, well, I'm going to open up more sites to carry more oxygen. And the hemoglobin next to that's like, oh, well, now I'm going to open up more oxygen sites. And so it's this snowball effect, if you will, right? The more oxygen that gets bound to the hemoglobin, the more sites will open up, and that's what causes that dramatic increase and ultimately that safety zone that we talked about. So the saturation of hemoglobin is ultimately affected by a patient's pH, their temperature, and 2 to 3 dpg. We just looked at this, right? So if their pH is off, their temperature is off, their metabolic rate is off, it's going to really affect the ability to carry oxygen. So if you have your patient that's really acidic, their CO2 level is really high, then their ability to carry oxygen to their tissues is going to be low, and they might go into failure, right? So when we're looking at this, we need to be cognizant of our patient's pH, their temperature, and their metabolic rate. And this is part of what we do as respiratory therapists. We look at this. We're part of this whole critical care team because we have specialty in this, and looking at their blood gas and looking at the relationship of the curve and what can we do to help this patient be more efficient with what oxygen they are getting in. Right? The other thing here is the total number of binding sites. If a patient's anemic, they're not going to have a lot of binding sites. So if we need to give them red blood cells, then that might be something that helps them get more saturation, more oxygen delivery to their tissues, right? So the number of red blood cells, right? If we increase red blood cells, we increase the ability to carry oxygen. So that's where we look at a patient's CBC. That's why it's important to look at other labs besides just your arterial blood samples, right? So when we're looking at those other labs, like the CBC, that gives us a red blood cell count and a hemoglobin count, that's going to help us figure out if our patient's anemic, right? Then we know that, hey, their hemoglobin is then we know we need to increase that. We know PRBCs, packed red blood cells, could be something that could help, or blood transfusion could be something that could help this patient come out of their multi-organ failure, right? As long as their heart's healthy enough to take that extra blood. When we're looking at oxygen in the plasma, what influences the amount of PO2 in the plasma? Well, a lot of stuff affects your P little AO2, right? A lot of stuff. So the condition of the inspired air, right? So this could be, when we're looking at this, this could be easily looking at something like high altitude, right? Where you have a lower barometric pressure, and you have a lot of pressure, even though you have the inspired air being the same concentration, there's less P big AO2 and therefore less P little AO2. Alveolar ventilation, how much are they breathing? Right? The more they're breathing, the more oxygen they can get into their tissues, the more CO2 comes off of the hemoglobin, the more oxygen can get onto the hemoglobin, and obviously the more oxygen that gets onto the hemoglobin, the more binding sites open up, right? And then we start that cascade. Diffusion, right? Easily, and this is where we see COPD and lung disease and all that bad stuff, fibrosis and syndromes like ARDS. That's where that kicks in. So if someone's P little AO2 is low compared to the P big AO2, that's where we start looking, is this a diffusion defect? Is there massive swelling? And then adequate perfusion. If your blood's not flowing to your lungs, if you're in right-sided heart failure, also known as cor pulmonale, right? If you're in that right-sided heart failure, you're not sending blood in the first place, or if you're hypotensive, right, low blood pressure, you're not going to be able to get that good diffusion, right? Because remember, in general, without lung disease, oxygen, right, going into the bloodstream is perfusion limited. I'll repeat that again. In general, without lung disease, oxygen going into the plasma, right, diffusing into the plasma, that P little AO2, is perfusion limited. So in other words, the faster the heart rate, the higher the blood pressure, the more oxygen, in theory, can get in there. That's why your response to hypoxemia, and hypoxia is going to be to increase your heart rate and your blood pressure. Your body's going to automatically increase your heart rate and your blood pressure to help increase the oxygen levels going into the bloodstream. Isn't that cool? So that's why you know, and we talked about this before, that's why you know if someone's heart rate and blood pressure are starting to come back down to a normal level after you've given them plenty of oxygen, that's a sign that you're being therapeutic. The oxygen level in their bloodstream is actually coming up. And yes, you can draw blood gas to show that, but you will know physiologically, hey, if those two things are dropping, if their heart rate and blood pressure is coming from a high state to a normal state, then that tells me that the oxygen level in their bloodstream is coming back up to a normal level, right? Because their body no longer has to work to compensate for that because you've compensated for it. So things that will go into alveolar ventilation is the rate and depth of breathing. If they took too much of their pain medicine, that could easily affect the PaO2, right? If they took a lot of pain medicine and they're hardly breathing, that's going to really affect it, right? That's going to decrease their oxygen level in their bloodstream. Airway resistance, we talked about this last chapter, as well as lung compliance. If those two are, if air resistance is high and lung compliance is low, we're not going to have good alveolar ventilation, right? Our alveolar ventilation is going to be very, very low. That's why someone in a severe asthma attack might have a low PaO2 because the amount of gas getting to the respiratory zone is very low, and their airway resistance is very high, and that's what's obstructing gas from flowing to the respiratory zone. Or let's say someone has pulmonary fibrosis and it's restricting the ability for the alveoli to stretch, right? So that would be a lung compliance issue. If I have low lung compliance, right, my lungs are stiff, it's going to make it hard for my alveoli to move a lot of gas and therefore cause a lower PaO2. What about my diffusion, right? So diffusion is a combination of surface area and distance. Okay, so surface area, this includes people that hypoventilate, right? That people that have atelectasis after, let's just say, an upper abdominal surgery. So here is my capillary, and here's my beautiful alveoli, but here's my atelectatic alveoli, and here's my capillary. I've decreased my surface area here because I'm not breathing deep. I'm on a lot of good medicines because I had upper abdominal surgery, a lot of good pain medicines that make me hypoventilate, and therefore I decrease surface area, and therefore my PA little AO2 is lower, right? So things like that could really decrease surface area on top of a disease like emphysema, where it just destroys that respiratory zone. Diffusion distance over there on the right. The thickness of the membrane, this could be due to inflammation, swelling, it could be due to scar tissue like we see in pulmonary fibrosis. That's a big issue here, right? So that's what we see with people that are in ARDS, is usually they're not only increasing the thickness of the alveolar capillary membrane, but also in ARDS, they're increasing the interstitial fluid that's being thrown into that alveoli as well. So their alveoli are pretty much, for the most part, filling up with pus, right? It's very disgusting, very gross, but it's something that we need to pay attention to, because what's going to be the ability for the PaO2 in ARDS if we have this going on? Well, their PaO2s are going to be very low. Well, why do I care about their PaO2s being low? If their saturations are fine, why do I care about their PaO2s being low? You should be like, Derek, I care about their PaO2s being low because that means that's what starts the cascade to the tissues. And that means their brain, their heart, their kidneys, their liver, all those vital organs, all right, those are just the ones I usually use. All those vital organs are being robbed of oxygen, because even though PaO2 doesn't carry a lot of oxygen, it starts the cascade to get the oxygen off the hemoglobin molecule, and I'll have hypoxic tissues if I don't have an adequate PaO2 level. So in something like ARDS, we try desperately to keep their AO2 above 55 if we can, as of recording this. If 60 would be great. If we can keep their AO2 above 60, that would be great, because we need to get oxygen to their brain. We need to get oxygen to their kidneys. We need to get oxygen to the heart to keep them alive, right? All right, past this slide. All right, so the curve, this is just going over what I've already talked through, right? Repetition, key to learning here. So oxygen attaches to hemoglobin, oxygen detaches from the hemoglobin. So that's where it goes on and it goes off, right? And so as I increase my PO2, as I increase at the lungs, so here's my lung tissue, and as I increase oxygen going into my plasma, as this AO2 increases, I will then increase the tension, right, being pushed onto the hemoglobin molecule, and then I'll have more open, more gradient that is available for more oxygen to be diffused into the plasma, which then means I'll have an increased plasma level, increased AO2, which then means there'll be more pressure pushing it onto the hemoglobin molecule, right? And that keeps going and going. So in order to get a high PO2, I need to get a high alveolar oxygen level. So in other words, if someone has a very low AO2, you draw blood gas out of their artery, and their artery level of oxygen is low, what's something you can do to help increase that level? Hey, increase anything that will increase their big AO2, right? FiO2, pressure, or get rid of CO2, right? That's where the alveolar air equation comes in handy. Just knowing it, you know the three factors that will increase P big AO2. Okay, so when we're looking at this, I can look at this. If I increase my P big AO2, then I therefore should increase my P little AO2. And if I increase my P little AO2, I should also increase my ability to carry oxygen on my hemoglobin molecule, because the higher the PaO2, the more pressure there is forcing that oxygen onto that hemoglobin molecule. Does that make sense? So the higher the P little AO2, the more binding sites, the more my hemoglobin want to carry oxygen. So hopefully that makes a little bit of sense there. Rewind it if you need to, take a break if you need to. It's a lot of stuff we're going over today. All right, so partial pressures. So the alveoli and the pulmonary capillary will then lead to the arterial, the branches, the tissues, the cells, the mitochondria. We need partial pressures of oxygen, right? We talked about this before. I need a pressure gradient between my capillary and my tissue, right? And if my PO2, let's just say, is 100 millimeters of mercury, I'll write T for Tor. Torricelli is the one that came up with millimeters of mercury, but you should use millimeters of mercury. I just don't have a lot of space here. So if my PaO2 is 100 millimeters of mercury and my pressure of oxygen in my tissue is, let's just say it's 40 millimeters of mercury, then I have a high pressure gradient and I'm going to send a lot of oxygen from the plasma into the tissue. Well, when oxygen that's on the hemoglobin molecule sees that there's oxygen from the plasma dumping itself onto the tissue, it says, hey, I want to join where you're going, right? If you're going somewhere, I want to go. It's like it's a kid brother, kid sister, right? If you're going somewhere, I want to go. And so it's going to pull itself off the hemoglobin molecule and also go into the tissue. So it starts that beautiful cascade of delivering oxygen to the tissue. So you need a good pressure gradient for that diffusion to start, or for that delivery to really go in there. That's great because the more oxygen you get rid of from the plasma and off of the hemoglobin molecule, that means these parking spaces of the hemoglobin molecule open up for CO2 to then park itself onto the hemoglobin molecule to get transferred to the lungs to get rid of. So this is a good cascade. This is a good exchange. Right? So this is something that we need to look at as far as the metabolic rate. We usually talk about the alveolar capillary relationship, but we also need to look at the tissue relationship, because remember, if this tissue is producing a ton of carbon dioxide, if this tissue is anoxic, right, it's going through the Krebs cycle, it's making an acid, just like someone doing wind sprints for an hour straight, it's producing lactic acid, it's going to have a big oxygen consumption and CO2 production, and we need to know if our patient's highly metabolic, is it something like an infection, right? What's going on? What's causing that? And that can really help us determine what our patient's needs and then start therapy as soon as we can. Right, so this is the picture from your book, much better than my drawings earlier. But when we're looking at just pressure, just normal pressure and how much oxygen that PO2 carries, look at this bottom purple dotted line that you see here. And I'll use purple here. You see this bottom purple dotted line that's in there? That's how much oxygen is carried even at 100 millimeters of mercury, right? Your body in the plasma, in the bloodstream, in the plasma, can barely carry maybe 5% saturation, right? Maybe saturation. So that tells you no matter how high someone's PO2 is, we need to be able to carry some on that hemoglobin molecule. The hemoglobin molecule does most of the carrying work. It's the most efficient at carrying that, right? If you take a little person, not like a little person, but if you take a human and you have a big pack mule, which one's going to be able to carry more gear up a mountain? Right? So the pack mule is going to be able to carry way more gear than the person traditionally because it has more ability to carry the workload, right? And so what you're seeing here is saturation would be your workload, would be the big one that can carry the workload. And then your PO2, it's important. It needs to be able to guide that pack mule. So in other words, PO2 guides the direction of oxygen going on to the hemoglobin and direction of oxygen coming off of the hemoglobin, right? We need that guide. And so that's going to be a very important part of this. So when we're looking at oxygen combined with hemoglobin, that's when we get our oxyhemoglobin dissociation curve relationship. The higher the pressure, the higher the saturation, right? Until we get to about 60, right? So when we're looking at 60, let's change to, let's see if green works out. So if we get to a PO2 of 60, our saturation should be roughly in the 90s, All right, that's perfect. So then we're looking over here at what's called that safety zone, right? So that means our ability to carry oxygen is going to be very good. We're going to have not so much change in our saturation for an increased pressure. So that's why we try to keep a patient's PO2 of 60 or above. Now, obviously, carrying too much oxygen is going to be a little bit dangerous as well. We can, especially with babies, they can get oxidative injuries greater than adults. And we can get decreased surfactant production as well as decreased mucociliary activity with high FiO2s and high PO2s. Babies are more prone to oxidative injuries, so they'll have a higher chance of retinopathy of prematurity and things like that. So we don't want it super high, but temporarily we can play with it a little bit. But we want to keep that PO2 above 60. Right, and that means our saturation should anywhere in here be in the 90s. That means we're carrying a good amount of oxygen. But remember our danger zone over here, right? Our danger zone over here says for a decrease, if we go from PO2 of 60 to PO2 of 50, then our saturation, if we have a normal curve, will go down to 80s. That means we're not carrying near as much oxygen to our tissues. If we go down to 40s, right? Then we'll go to a saturation of the 70s, right? Not near as much oxygen, and so on and so forth, right? When you look at this, when we get to a PO2 in the 30s, right, we barely have a saturation of 55%. How long do you think your tissues can survive with the saturation of 50%, right? You're not going to deliver near as much oxygen in that case. So you need to be cognizant that we need both saturation and pressure for this normal relationship, for this normal ability to provide your tissues with oxygen. So left shift, right shift, this is something we've already talked about. Much better picture than I was able to draw. And this is where we talk about at the lungs, your body naturally is actually left shifted at the lungs. You have low hydrogen ions, low temperature, low metabolic rate. So at your lungs, your body's going to want to carry a lot of oxygen for a low pressure. This is good, right? Because you have a low pressure of oxygen from your venous system coming to the lungs. And so that means once that CO2 is dropped off that hemoglobin level, right? Once that CO2 is dropped off of the hemoglobin into your lung tissue, then you're going to have a lot of room left over for oxygen. So it's going to want to attach itself there, right? And that's what's going to change the shape and increase the saturation. So at my lung level right now and at your lung level right now, you are actually left shifted. That's perfect. We want that. That means if in theory we go to the tissues, now that same blood cell, that hemoglobin molecule travels to your tissues. At your tissues, you have high temperature, high metabolic rate glycolysis, right, 2 to 3 BPG, and then low pH or high hydrogen ion levels, right? Then your hemoglobin's going to change shape and dump off that oxygen. Right? It does that so it actually can change shape and actually pick up CO2. So it does that on purpose, not only to dump off oxygen, but also to pick up CO2. So your body naturally moves from a left shift to a right shift depending on where it is. If you're in the lungs, you're left shifted. If you're in the tissues with high metabolic rate and temperature and more of an acid level, then you're going to be at a right shift. And that's perfect. You want your tissues to be right shifted because that allows for more oxygen to be delivered, more oxygen to be unloaded to the tissues. In your lungs, it allows for more oxygen to be combined to the hemoglobin because with the left shift, you love oxygen. So left shift loves oxygen. Right, left shift is where you wear your wedding ring. It's a left shift loves oxygen. Once it attaches itself, hemoglobin attaches itself to oxygen. When it's left shifted, it won't let it go. And you want this in your lungs because do you want the oxygen going to the hemoglobin molecule and then back into the lungs? No, you want the oxygen molecule staying on the hemoglobin for the journey to the tissues. Okay, so in your lungs, you'll be left shifted. It will hold on and not let it go. So if someone's left shifted and they go to the tissues, remember there's no pressure gradient there, right? Because they're left shifted, they have a low pressure. which is the important part, that pressure gradient. If there's low pressure and high saturation, the hemoglobin's like, I love my oxygen and I'm not letting it go. There's no one going into the tissue, so I'm not going to go into the tissues either. So I'm going to hold on to it. So that's a good thing. You want your lungs to be left shifted so that way the hemoglobin attaches itself with the oxygen and doesn't let it go until it gets to the tissues, where the tissues are right shifted. So when someone's right shifted, it actually increases the affinity for oxygen to be released. So as that same hemoglobin molecule travels from the lungs to the tissue, it's going to have a higher affinity when it reaches that lower pH. When it reaches that higher temperature, it's going to change the shape of that hemoglobin, and it's going to, whatever oxygen is on there, dump it off. It's going to get rid of it. So this is perfect. In your lungs, you'll attach it like a magnet and won't let it go. And at the tissues, your hemoglobin's like, I'm done with you. I've taken you this whole journey. I'm giving you to the tissues. I'm done with you, right? And so it's going to have that different relationship. It's going to release. So you have a higher affinity to release oxygen with a right shift. You have a higher affinity to hold on to oxygen with a left shift. So hopefully you got that down. And here's the picture of the P50 as well. Remember, the P50 is defined as the pressure at which the saturation is at 50%. So normal P50 should be 27 millimeters of mercury. So at 27 millimeters of mercury, your saturation should be 50%. If I tell you someone's P50 is at 40 millimeters of mercury, you should tell me that's a right shift. That's a right shift because I have a higher pressure and a lower saturation, right? The P50 is still 50%, but now it takes me 40 millimeters to do this. So this is actually a right shift of the curve. If I tell you someone's P50 is 10 millimeters of mercury, you would say they're left shifted because there's an increased saturation, right, for a lower pressure. So that would be a left shift, right? If there's an increased saturation for a lower pressure. So P50 less than 27 equals left shift. P50 greater than 27 equals a right shift. Now remember, if someone's shifted, the therapeutic thing to do is give them more oxygen. In fact, the board exams, that's the question they want you to answer. Hey, your patient is shifted on the curve. What do? Your answer, and you're learning it now, is going to be give them more oxygen, right? So in the meantime, give them as much oxygen as possible until we figure out, hey, is this a massive infection that's causing an increase in metabolic rate and temperature, right? And that's also metabolic rate is meaning my CO2 production is increasing, and this is our carbonic acid, which would then make my pH decrease, right? So anything that's over here would cause a right shift. So therapeutically, increase the oxygen. But understand, that's why I used hydrogen ions for this. See how everything on the right shift is increased. Increased DPG or BPG, same thing. Increased temperature, increased CO2. And I also put an increase in hydrogen ions. Right, that means anything that's increased would be a right shift. And then therefore, that's why instead of doing pH, I did hydrogen ions. H+. All right, then therefore anything that's decreased would be a left shift, right? Low hydrogen ions, which would be an alkalosis, low CO2 levels, low temperature, low DPG, BPG, fetal hemoglobin. Fetal hemoglobin would be high, but that's if they're baby. So as far as looking at these, fetal hemoglobin, carboxyhemoglobin are sort of exceptions there. But if you're looking at anything that's high, as far as temperature, metabolic rate, CO2, hydrogen ion level, that's all right shift. Anything that's not there would be a left shift. What about met hemoglobin, right? What about dysfunctional hemoglobin? Well, actually, dysfunctional hemoglobin would also be a left shift because that really changes the functionality of the hemoglobin. So what oxygen is on the hemoglobin molecule won't want to let it off. So if you're asking, if you're curious, and I know you guys are, if you're curious about what happens with dysfunctional hemoglobin in general, usually that will become a left shift, even with methemoglobinemia. Okay, so let's go through some examples here. So some examples. If I have a P big AO2 of 60 and a little AO2 of 60 millimeters of mercury, right? So that's great diffusion, right? My hemoglobin will be 90% saturated as it leaves the pulmonary capillary. Does this agree, right? If I have a PO2 of 60, should I have a 90% saturation? Well, is there a rule that I taught you guys, or that's also probably in your books as well? 4, 5, 6, 7, 8, 9. So if I have a PO2 in the 40s and I have a normal curve, my saturation should be in the 70s. Same thing with PO2 in the 50s, my saturation should be in the 80s. PO2 in the 60s, my saturation should be in the 90s. So in this question, it's asking if I have a PO2 in my 60s, right, 60 millimeters of mercury, should I have 90% saturation? Well, if I have a normal curve, a normal relationship, in other words, I don't have an acidosis or carboxyhemoglobin, right? None of that's going on, then yes, this does agree with the oxyhemoglobin dissociation curve. Do you see how I check that? So one of the things that you look at when you get an arterial blood gas sample is actually the curve, right? Are they shifted? Do I have a normal pressure? Do I have a normal saturation pressure relationship when you're doing this? So this does agree. This person is not shifted on their curve, and they're actually carrying a good amount of oxygen to their tissues. Good job, person. All right, we have a patient that has a P big AO2 of 60 and a little PaO2 of 60. Okay, but we have an increased CO2 and the pH is lower, which means hydrogen ions have increased. I'll repeat that. Increased hydrogen ions, increased CO2, and their saturations are low. Their saturations are 75%. So are they shifted? Well, how do I check if they're shifted? Let's look. 4, 5, 6, 7, 8, 9. So when we're looking at this, so their PO2 is 60, but in their saturations, if their curve was normal, should be in the 90s, but instead we have a saturation in the 70s. So I have a good pressure for a low saturation. Well, this is a right shift, right? Good pressure, low saturation. I'm not in my safety zone, right? When I should be in my safety zone, I'm bringing my danger zone, my vertical danger zone has been shifted to the right. Great. That means my patient's not getting near as much oxygen to their tissue. So this is a right shift of the dissociation curve. Remember, anything that's increased is a right shift. Increased hydrogen ions, which is a low pH, increased CO2 level, increased temperature, increased metabolic rate, 2 to 3 ppg. Those are all right shifts. So when you've seen those that are increased, that should have tripped you that this patient could be right shifted. So what's the therapeutic treatment for this patient? Give them oxygen and then figure out what's causing the right shift, right? So this person has a CO2 and a low pH. So my question here would be, is this patient hypoventilating? And if we put this patient on a ventilator to restore ventilation, alveolar ventilation, then we should be able to fix this curve from being abnormal. All right, we have a new patient. All right, their PaO2 is 60, their P little AO2 is 60, and we have a drop in their cardiac output and subsequent increase in their pH, and their hemoglobin is 95% saturated as it leaves the pulmonary capillary bed. So is this a normal relationship? So let's check it. PO2, saturation. 4, 5, 6, 7, 8, 9. All right, so this patient has a PO2 of 60, And then their saturation, PO2 is about 60. And we've had a drop in the cardiac output and an increase of their pH to 7.6. So the hemoglobin is 95%. So here we have a normal relationship. So PO2 in the 60s, sets in the 90s. But notice that we're setting pretty high in the 90s. We're in the 95% range for a PO2 that's barely 60. So PO2 that's 60. So that means that we have a higher saturation for a lower pressure. We have a higher saturation for a lower pressure. Also notice what else is going on here. Their pH is 7.6, which means their hydrogen ions are decreased. So which shift is this? I have a high saturation for low pressure and I have a decreased level. That would be a left shift. Well, there you go. What would you do for this patient? Well, left shift sounds good because their saturations are great. But what happens at the tissue level? Remember, the tissues, they don't want to drop off a lot of oxygen if there's a lower pressure. So in this situation, we want to restore a normal pH, and that should help change the shift to a normal, or change the curve to a normal level. So the Bohr effect, and I'll try to keep it as simple as I can here, and we'll go into more detail when we talk about the CO2 dissociation curve. But when we're looking at the Bohr effect, we're looking at the sort of cascade term. And so it's a term used to describe the effect of CO2 and pH that changes the hemoglobin's ability to accept or get rid of oxygen. So in the lungs, and that's what you're looking at on the screen here. So in the lungs, you have high oxygen levels and low CO2 levels and high pH. Remember, we're left shifted in our lungs, right? Left shifted in our lungs. So this means that we're going to have a higher affinity to bind oxygen onto the red blood cell, onto the hemoglobin molecule. So the Bohr effect in the lungs, when you're left shifted, says I'm going to increase my binding affinity. I'm going to have an increased affinity to bind oxygen, right? So we don't want the oxygen to bind to the hemoglobin and then just distribute itself back into the lungs again. We want it to go to the hemoglobin and stay on the hemoglobin until it travels all the way down to the tissues. So we need to be left shifted at our lungs in order to transport the bulk amount of oxygen. So the Bohr effect says I'm going to have an increased affinity in my lungs because I'm left shifted to bind oxygen. It's going to have a very hard time coming off of there, which is good in our lung tissue, right? But where would it be bad? Well, that would be bad at our tissues. If we were left shifted at our tissues, that means the hemoglobin is not going to let go of that oxygen. It loves that oxygen so much, it's not going to let it go. So we need the lungs to be left shifted, but we don't need it to be left shifted at the tissues. And that's when carbon monoxide poisoning means that that hemoglobin left shifted at the tissues, and it's not going to let the oxygen go. Right? It's going to be very, very poor, right? So what the Bohr effect, it's that cascading. It means I'm going to hold on to it when the pH is high. I'm going to hold on to it when my CO2 is low. I'm going to hold on to it when my oxygen level is high. That's my Bohr effect in my lungs. Okay, but or left shift, as I get to my tissues, this is going to be a right shift, right? So as I get to my tissues, where I have less oxygen levels, where I have CO2 being produced, where I have pH being decreased because I have metabolic rate, right? My higher 2 to 3 BPG, DPG. When we're looking at that, the Bohr effect says, oh, in this environment, I want to dump off the oxygen. I am no longer wanting to carry this oxygen. So it's a cascade effect to get rid of oxygen. So depending on the environment, so up here with a left shift environment and down here with a right shift environment, up here with the left shift environment, the Bohr effect says I want to attach oxygen. Down here with the right shift environment, I want to dump oxygen, right? I no longer want to carry it on the hemoglobin molecule. So this is the Bohr effect. So we'll go into more detail when we talk about the CO2 dissociation curve, but just wait on that, if you will, for me. All right, so this is what we're looking at. I like this computer drawing. This is what was used in my class when I was a student, so I have no clue how classic this picture is. But when you're looking at it, this is just a different way to look at it. When you're breathing in, you're getting that good oxygen to your tissues by sending it to your lungs, and then your lungs pick it up. And you already have some CO2 from your tissues, right? Some CO2 that stays in there, and it carries it just like train cars to your tissues. Now, if you have very low metabolic tissues, it's not going to dump it off, but very high metabolic tissues, you're going to consume more of this oxygen that gets dumped there. And as a result of all this oxygen that gets consumed here, it's going to produce all this CO2 that then gets put into your hemoglobin boxcars and then transported those boxcars back to your lungs where you get rid of it, and so on and so forth. So this is sort of that cycle that you can go through. So just imagine that picking it up, and these little boxcars that you're seeing here are your hemoglobin that's carrying or transporting most of this. And then you have your heart sort of pumping it over here, and that heart looks like it's working hard. Good job, heart. So in summary, the CO2 or the oxygen dissociation curve is not linear, right? Remember, we have this sort of Bohr effect that goes on. The more oxygen that's in the plasma, the more oxygen binding sites will open up and changes the shape of the hemoglobin molecule, the more sites will develop. And that's why we have a dramatic or an exponential change in this relationship. So it's sort of like peer pressure. Hey, one person sees you do it, then 3 people want to do it, and then 9 people want it, right? So it's more of that snowball effect, if you will. All right, so at higher saturation levels, that curve is flat, so we're not going to see a lot of change for a little change in our pressure. We're not going to see much change in our saturations, right? And then if our PO2 is less than 60, we're also going to have an issue where we're going to have dramatic changes in our saturation levels with a PO2 less than 60, assuming a normal curve. So at high saturation levels, the curve is flat. Below the levels, the PO2 declines sharply. So if I have a saturation of 75% and my PO2 is at 47, this is going to mean that I'm going to have a very low pressure. I'm going to have a very hard time getting oxygen to my tissues. So the position of the curve can shift right or left. Remember, left shift, you have a high saturation for lower pressure, and it's inverted for the right shift. So if you got one of them memorized, the other one's just the opposite. Okay, so I don't know if that helps you or not. Active muscles, they're going to need a lot more oxygen, right? If you're running up and down stairs or anything like that, you're going to consume more oxygen because your tissues need more oxygen. You have a higher metabolic rate. You're using more glycolysis, right? So heat, exercise, acidosis, hypercarbia, which is high CO2 levels, increased 2 to 3 DPG, all cause you to shift to the right. So if you go and work out right now, go do a Zumba class, right? Really, really hard, you're going to go into that sort of that right shift at the tissues, and you're going to consume more oxygen, which is good because remember, as the blood goes to the tissues with the Bohr effect, we're going to dump off more oxygen. So this is good. This is how your body normally functions. If your activity is minimal, or if you're outside in cold weather and you're not shivering, right? Assuming you're not shivering, right? Your tissues are going to be cold, more alkalotic, hypocarbic because you're not producing a lot of CO2 because your metabolism slowed down. 2-3 DPGs low, so you have more affinity to hold on to oxygen, and you're going to be more of that left shift. So the presence of fetal hemoglobin and carbon monoxide will cause a left shift of the curve. Those are just 2 exceptions to this whole thing, but understand what happens with alkalosis, with low temperature, low metabolic rate, right? Low 2 to 3 DPG, low hydrogen ions, low temperature, and low metabolic rate. All right. So hopefully, if you need to take a break, take a break. Come back to it. I love this because you can speed me up, you can slow me down, you can take this in chunks. You don't have to worry about getting distracted as far as this goes, and you can slow it down or speed it up and re-listen to it. So let's move on to transport information. Okay, so oxygen delivered might be lower than is indicated by the pressure when you have a disease that causes the curve to shift. And we already talked about this. If you're right shifted or left shifted, your ability to get oxygen into your tissues decreases. So if you have a right shift, whether it's a decreased cardiac output or a decreased level of red blood cells, like a patient's anemic, or the patient's ability to carry oxygen is very diminished, right? It's not going to be able to deliver a lot of oxygen, right? Especially if the cardiac output is low, our ability to send that blood is low. It'd be like driving a golf cart across country. There's some delivery, but it's very low and minimal, and it's not going to get the job done compared to a giant trucker, right? Big difference. So we've learned how to figure out how oxygen gets into the blood, how it diffuses into the plasma, and how it binds to hemoglobin. But now we need to look at how it gets transported around the body, right? How much oxygen is in the blood. So this is where we look at more calculations. I know you're like, Derek, this is great. I love math and love calculations. Understand these will help you not only understand physiology better, so concept based, but you will also use these in critical care medicine, and I have used them personally in critical care medicine to help discover how sick a patient is and if the risk versus benefit are good for a patient and where the problem is and where we should focus our efforts. I have used these calculations personally, and there are physicians that also use these calculations. So this is not something that we're just teaching because. This is something that we're actually teaching with a purpose, because you will use these, especially if you want to work in critical care medicine. So this is going to give you much more detail than your CCO2, your CaO2, and CVO2. I can have a really beautiful CaO2, but if my heart's not pumping it to get to the tissues, then that's what's causing my tissue hypoxemia, right? I'm not sending that good blood to my tissues, right? So then it tells us to work on cardiac issues, right? So this is where we'll start. Right? So mathematically, we can manipulate CO2, CVO2, and CCO2. We have already talked about these three. So these are great. But there are 6 transport calculations that we can then look at and see, hey, is there more problems going on? And it can actually help us focus onto a specific area to help our patient out. So the first one is going to be DO2, or delivery of oxygen. I like this calculation because it's just adding your cardiac output to the whole, or sorry, factoring the cardiac output into your delivery of oxygen. So it's called DO2, or delivery of oxygen. You're going to take your CaO2 times 10. Notice this is in parentheses. So you're just going to put a 0 onto the CaO2. You didn't hear that from me. So you're just going to take the CO2 times 10, and then you're going to multiply that by the cardiac output. So remember, you always do everything in the parentheses first. So PEMDAS when we're doing this. So CO2 times 10 times the cardiac output. You might be asking, and some of you might, is where does the 10 come from? Well, I have 2 answers for that. If you are a person where math gives you anxiety, I will tell you it's magic. Pure respiratory magic. If you are a person that doesn't believe in respiratory magic, which why are you in this program? I'm just joking. If you want to know more detail why that 10 is there, it is a conversion factor. Cardiac output's in liters per minute, and this is in mLs per minute, so that's a conversion factor, right? CO2 is volumes percent. So this will convert it to mLs of O2 per minute ultimately. So how much oxygen gets to the tissues? So let's do look at certain things that affect the DO2 before we start calculating it, right? Let's look at factors or what can change your delivery of oxygen. So this looks at three things: your ability to oxygenate the blood, right? Your hemoglobin concentration, as well as the function of your heart, your cardiac output. Things that will decrease your delivery will be a low PO2, right? So let's say you have a viral pneumonia, which is why you have a low PO2. Well, that will decrease the delivery to your tissues. Or let's say you have decreased hemoglobin, like you're anemic, or you have a low saturation because your PaO2 is low in the first place, right? So that could also be a reason why their delivery of oxygen to the tissues is low. Or it could be because your heart's not functioning. A decreased cardiac output. QT comes, I like to use QT for cardiac output because CO is carbon monoxide. So I like to use QT as cardiac output because it actually represents the QT segment of an EKG or ECG. So decreased cardiac output could easily cause low delivery. Like I said before, I could have a CaO2 of 20 volumes percent. But if I'm not pumping it, if my left ventricle is very sick and it's not squeezing the blood very hard, then I'm going to have a low ability to deliver it to my kidneys, to my brain, so on and so forth. So what's a normal adult cardiac output? And hopefully you guys already remember this. Somewhere between 4 to 6 liters per minute. Right, so we'll just say perfect in the middle is 5 liters a minute, right? Depends on the patient's body surface area when you get down to the more details when we'll look at that. But a normal cardiac output is roughly between 4 to 6 liters a minute. So if someone's blood pressure is low, but we're delivering lots of oxygen, they don't have anything wrong with their pulmonary capillary space, then that might be the area to focus on. We need to focus on getting the heart to pump more efficiently. Well, if their heart's super sick, then we might need to do something like VA ECMO and bypass the ventricle, or do a balloon pump and help the blood pressure, right? Things like that. Ultimately, so trust me, these will come in very handy, and they're advanced concepts, so take it slow, but you'll get there. So when we're looking at this, DO2, and this is us doing the math part. Okay, so the previous screen was us looking at sort of the concept and what can affect it. So you're like, hey, let's just do the math. Okay, here it is. If I have a cardiac output that's perfect, let's say it's 5 liters a minute for an adult, and I have a perfect CaO2, let's do this together. So a normal CaO2, and this is the calculation, cardiac output times CO2 times 10. Remember, CO2 times 10 is in the parentheses, so we're going to do that first. So normal CO2 is 20 volumes percent times our continuous 10, right? So this would be 200, because remember, we're just adding a 0 to this. What's 200 times 5? So what's 200 times 5? So 200 times 5 is 1,000. So 5 times 2 is 10, and then we're just going to add the zeros. So that's 1,000 when we get to it. So when we're doing 1,000 milliliters of oxygen per minute is what's being delivered to our tissues, which is the same thing as 1 liter of oxygen per minute. So is this a normal value for this? All right. So what did we plug into this? Cardiac output's 5 liters. Is that a normal value? Yes. CO2 at 20 volumes percent. Is that a normal value? Yes. So is a normal DO2 1,000 mLs of oxygen per minute? Yes. Right? So here's an example for us to do together here if you want some more practice. And then, of course, do the worksheets too, right? There's a worksheet 4 that goes over this as well. So if I have a DO2, what if my cardiac output's 4 liters a minute and my CO2 is 16 volumes percent? Oh heavens. All right, so what am I going to do here? I'm going to take my 4 liters, and then I'm going to look at my cardiac output is 16 volumes percent times 10. So this would be 160 times 4. should equal 640 mLs of oxygen per minute. Which tells you what happened to this patient's delivery of oxygen when their cardiac output and their CaO2 decreased. Well, it decreased as well. We're only delivering 640 mLs of O2 per minute compared to 1,000 mLs of O2 per minute. So when we're looking at this, you see that this patient's ability to deliver oxygen decreased if their cardiac output dropped as well as their CaO2. Well, cardiac output is still within normal limits. Let me ask you on this patient, which problem would you want to work on first, their cardiac output or their CaO2? Well, looking at this individual situation, still this is within a normal value for cardiac output. So which value is outside the normal limits? Right, your CaO2. So I need to figure out what caused my CaO2 to be low. So this could be anemia. This could be a diffusion, this could be hypoxia, like a low P big AO2. So those are all things that we should be looking at. Okay, so hopefully you got the DO2 calculation. Write that down, put the normal next to it, don't forget the units. Those are all things that you need to know. This next calculation, calculation number 2, is your A to V difference. You're going to love this one. Right, this is one of my favorite ones because this is just asking what your CaO2 is minus your CVO2. What's the difference between your arterial content and your venous or mixed venous content, right? So the difference between CaO2 and CVO2, all you do is you subtract them. You take your CaO2 minus your CVO2, and then there you go. And this is, as we've talked about before, is how much the tissues use up when it goes through when the oxygen goes from the arterial back to the venule to the vein ultimately. So how much oxygen did the muscle consume as far as CaO2 is concerned and CVO2 is concerned? It consumed roughly, usually around 5 volumes percent, right? Because a normal CaO2 is 20 volumes percent, a normal CVO2 is 15. So when we take 20 minus 15, the difference is 5 volumes percent. So that means 5 mLs of oxygen are extracted from each 100 milliliter sample of blood that goes through the tissue for metabolism. Right? That's it. Right? 5 milliliters. So that's all that's saying ultimately is how much is left over, how much is pulled away after the tissues have used it. So we're only using about 5 volumes percent, which is great. So when the patient starts exercising, when you start exercising, your CVO2 will go down, right? Because your metabolic rate's increasing. So your A to V gradient would increase. So the bigger the gradient in your A to V difference, the more the metabolic rate usually. Love this equation because it's just the subtraction. So your answer is going to be in volumes percent because we didn't change anything, right? CO2 is in volumes percent, CVO2 is in volumes percent. So your answer units will be in volumes percent. What are some factors that can alter this? Well, we just went over sort of the beginning of the equation, which is great. Now we're just looking at sort of, hey, what can make this go off? So if I have a patient that has a increased A to V gradient, what would cause that? What are some things that can rule out or think about? If a patient is exercising, so we'll see this with, if you do diagnostic studies and you put these people on these treadmills or on these bicycles, these high performance athletes, you can see when they hit their lactic acid, or you can see when they hit that lactic level. Pretty cool stuff. You can see it if someone's seizing, that'll increase the gradient because their muscles are working overtime. Shivering, muscles are working overtime. Hyperthermia, muscles consuming a lot of oxygen and producing a lot of CO2 overtime, or even a decreased cardiac output. What is that doing there? Oh heavens. I hope you are asking, why would a decreased cardiac output factor in to an increased gradient. Well, remember we talked about dwelling time of the blood through the lung tissue and how it only takes like 1/4 of a second, and you have up to 3/4 of a second to get that oxygen and CO2 to diffuse. Hopefully you do. If not, go back and watch those. But when we're looking at the tissues, the longer the dwelling time, in other words, the lower the cardiac output, the lower the blood pressure, the longer that blood spends going to that tissue. The longer it spends there, the more oxygen the tissues are going to extract. So that means if someone has a decreased cardiac output or a low blood pressure, let's just say, as a good example, the more oxygen it robs because it just has more dwelling time there, and it's going to be like, oh, you haven't gone by yet, I'm going to take more oxygen. New blood hasn't come in yet, I'm going to take even more oxygen. New blood hasn't come yet, I'm going to take more oxygen. And it keeps taking and taking and taking until new blood shows up. So that will increase the gradient. Hopefully that makes sense. All right, what about increasing? What about decreasing the A to V gradient? So things that can easily do this, and we actually may do this on purpose too, skeletal muscle relaxation. Skeletal muscle relaxation is going to be a big one because if we have a patient that has very low PaO2s and has very low saturations, one of the therapies that we can do, or one of the interventions that can be done, is giving them a paralytic. Why would we paralyze them? Well, they're already on the breathing machine. What happens to their metabolic rate if we paralyze you? What happens to how much oxygen your tissues are consuming if we paralyze your muscles? In other words, your muscles aren't being used. So the oxygen consumption of your muscles decreases if we paralyze you. So if you are paralyzed, your A to V gradient narrows. So your CO2 might be 20 volumes percent, then your CVO2 might be 17 volumes percent or 18 volumes percent. So this is actually something we can use for people that have really low oxygen levels, is actually give them a paralytic agent to help get more oxygen to the organs that actually need it and keep them away from going to the oxygen away from going to tissues that don't need it for life function. So do I need my leg muscle to keep my body alive, or would I be better off sending that oxygen that normally would have gone to my leg muscles to my kidneys or to my brain or to my heart or to my lungs for metabolic usage? Which I would rather have the oxygen be sort of focused in the areas that are going to keep the patient's brain, heart, lungs, all that stuff alive than on their calf muscle, right? No matter how good their calves are, I'd rather focus on keeping their brain going. Peripheral shunting, this happens with cold weather. This is actually something your body does. You know how your fingers and hands turn like that bluish, grayish, purple model type thing? That shunting that happens where you vasoconstrict in cold weather, that's what you're doing there. So if you vasoconstrict, you're decreasing blood flow to that area and therefore decreasing oxygen usage or decreasing your metabolic rate in that area. Poisonings can do this. Cyanide poisoning could easily do this. Hopefully you won't have to deal with that in your career. May decrease the A to V gradient. And hypothermia, and this is what I was talking about with the shunting, right? Low core body temperature. That can easily decrease the A to V gradient. Now remember, okay, what's number 5 here? It says increased cardiac output. What is the deal with that one? You should be like, Derek, you already explained this. I got this, I'm a pro. So with an increased cardiac output, let's just say it's an increased blood pressure, right? With this situation, I have blood moving through this alveolar capillary membrane, or it's not alveolar, this tissue capillary membrane really, really fast. It's shooting right through it. It does not have a lot of dwelling time. So therefore, the oxygen extraction is going to be very minimal. As it goes past there, it's not going to have a lot of time to pull that into the tissue and therefore may decrease that A to V gradient. Hopefully that makes sense. It doesn't have enough time to rob the blood of oxygen. Therefore, it's going to be a decreased A to V gradient. Hopefully that makes sense. All right. So we've talked about the A to V gradient. Now let's look at another calculation. So put another spot on that 3x5 card or that big page by this point of another calculation. This is our oxygen consumption, or our VO2. And the way I always like to think about this is Pac-Man or Miss Pac-Man, whichever one you like, because this is where you're going to look at the consumption of oxygen. I always think of Pac-Man or Miss Pac-Man eating oxygen. So that's where I see the VO2. I think of Pac-Man. I don't know why. That's just how my brain remembers it. And this is how much oxygen the tissues extract in 1 minute, or how much uptake they have, right? That's another term that you see. There's a term called Vo2 Max, and if you have like a Fitbit or any of those fancy oxygen or fancy smartwatches or devices, they might talk about Vo2 Max, which is like how healthy an athlete is, or how healthy your body oxygen demands are. And this is what you'd be looking at here, is how much oxygen gets used between the arterial and venous side. Wait a second, we already did this. But this time, right, this is our A to V gradient, but this time we're factoring in the cardiac output. So in this situation, we're taking our A to V gradient times our cardiac output times 10. Okay, so here's the thing. The major difference between our consumption and our A to V gradient is we're looking at how much in percentage wise, or how much gets consumed by the tissues in a percentage. So instead of just looking at in volumes percent, how much percent overall are my tissues consuming? So that's why we have the example here. So look at this example. If I have 100% saturation on my arterial side, so in other words, you draw an arterial blood gas, and it says you have 100% saturation of oxygen on your hemoglobin. Great. And then you draw a venous sample, a venous blood gas off of a central line, let's just say, and it says you have a venous oxygen level of 75%. Well, what's my consumption? How much percentage, just percentage, not volumes percent, but how much just percentage of oxygen was consumed from my arterial to my venous side? Well, when we're looking at this, that would be 25%. My consumption of oxygen is 25%. So this is the change that causes our CO2 to be in 15 and 20 and 15. Some people may not respond to this. Hey, their normal A to V gradient is 5 volumes percent, and now they're at 7 volumes percent. That may not transfer over to a lot of critical care situations. So one of the things that they might ask you to do would be like, hey, how much oxygen is their body consuming? So we know that, hey, in this situation where it's 100% on the arterial side and 75% on the venous side, that their body's consuming 25% of the oxygen we're delivering. Does that make sense? Their body's consuming 25% of the oxygen that gets delivered to the tissues. So this looks at it in a different way. It's a different way to look at the A to V gradient that a lot of people think is a lot easier to understand, because how much just generic percent-wise of the oxygen are we delivering is getting consumed? In this situation, 25% of it, which would be normal. So let's calculate it. Okay, so we've gone over the concept. The concept is out of how much oxygen gets delivered, what percent of it gets consumed, right? If I'm delivering 100% and my venous is 75%, that means my body is consuming 25% of the oxygen that goes by my tissues. Okay, so let's calculate this. Okay, and here it's drawn out for you. I love it when we've thought ahead this far. So it's your A to V gradient times your cardiac output times 10. The 10, once again, is a conversion factor, because remember, your A to V is in volumes percent. And so that's a conversion factor that turns this, and then your cardiac output's in liters per minute, so that turns this into mLs per minute. Oh, isn't this fun? All right, so when we're looking at this, our normal A to V gradient is 20 volumes percent minus 5 volumes percent, right? So this is a gradient of 5, okay? So 20 minus 15 is 5. So 5 volumes percent times 5. What's 5 times 5? 25, and then when you multiply anything by 10, you're just adding a 0 to the end of it. So that means our A to V gradient is, or not A to V gradient, our consumption is 250 mLs of oxygen per minute. So would that be normal? Well, let's look at the equation. Is 20 volumes percent normal for our CO2? Is 15 volumes percent normal for our CVO2? Is 5 liters a minute normal for our cardiac output? Yes. So your normal value for oxygen consumption is 250 mLs of O2 per minute. Okay, so let me, before we go on to this next math problem, let me ask you this. What's your normal DO2? Oh heavens, you might have to stop, look down at your papers. Hopefully you're taking notes. Normal DO2 is 1,000 mLs of oxygen per minute. Your normal VO2, or consumption of oxygen, is 250 mLs of O2 per minute. So that means we have left over 750 mLs of oxygen per minute. So that means we had a lot more room to consume more oxygen. So this means I may not have to change my cardiac output. I may not have to change a lot of stuff if I get up to go walk to the bathroom and back, or get up and go to the store and back, right? As long as I'm not vigorously exercising, my DO2 is more than efficient at delivering my tissues what they need for metabolic process. I have left over 750 mLs. This would be like getting a paycheck and then you pay all your bills and you have a lot left over. You have a good buffer left over, right? This would be nice, right? And that's what's going on here. So you're delivering 1,000 milliliters and you're only consuming 250 mLs. That means you have 750 left over. Okay, so that is more just me trying to hammer the concept down of what VO2 is compared to DO2. So DO2 is we're delivering this, and then how much are we consuming after we deliver it? And then these are our leftovers that we'll put in the fridge for a rainy day. I don't know. So when we're looking at this, let's try a different, plugging in different values. So let's try all the normal values, except this time our cardiac output, we're going to increase it. Okay, so 20 volumes percent, normal. 15 volumes percent, normal. But then we go to the higher end of normal for cardiac output. So 20, so we have 5 volumes percent, 5 volumes percent, right? So down here, I'll just do it here. So we have 5 volumes percent times 6 times 10. Okay, what's 5 times 6? So this would be 30, right? 5 times 6 is 30. So 30, add a 0 behind it, that would be 300. So this is going to be 300 mLs of oxygen per minute. So what happened with our consumption? Did it increase or decrease? Well, we have a higher number, so our oxygen consumption increased, which means more oxygen is being extracted. Why? Why is there more oxygen being extracted when all that changed is a higher blood pressure or a higher cardiac output? Well, let me ask you this. Is there a muscle that is working harder when we change this factor? So remember, the factor that changed was the cardiac output. So the heart is working harder, and therefore, do you think that your metabolic process of your heart's oxygen consumption would go up? Therefore, your total oxygen consumption would also go up. I hope that makes sense. So this means that our heart's working harder and it's consuming more oxygen. Their heart is requiring more oxygen to keep up its metabolic process. Isn't that crazy? So what are some factors that can change our consumption? So you're going to see a pattern here, and you're going to love patterns because patterns make things go a little bit simpler, a little bit easier to remember. So when we're looking at this, things that will increase consumption of oxygen would be exercise, right? Your body needs to consume more oxygen to avoid anaerobic metabolism, unless that's your goal. Seizures, of course, if a patient's shivering. Hyperthermia, like infection, things like that. Things that can decrease, of course, paralytics, like skeletal muscle relaxers. Peripheral shunting, like the vasoconstricting when your fingers when you're cold type thing. Some poisons can easily do this. And then hypo, so low core temperature. Thermia, right? Found outside, not shivering. Right, that's why I say not shivering. Found outside, not shivering. Right. That's why if we used to do hypothermic therapy, as of recording this, hypothermic therapy is where we take their core temperature less than 30, around 33 degrees centigrade or so, and it takes them down a little bit, and we have to paralyze them so that way they're not shivering, and then therefore voiding the hypothermia part. And you can do some research on that process overall, but that hypothermia will decrease our consumption. All right, so when we're looking at this, there is an option, and I'm not going to stress this for you guys at all, but I want you just to be aware that it exists. This is sort of bonus material. So when we're looking at this, Vo2 consumption is usually related to a patient's body surface area. And so the bigger the patient, the more extraction they can do. So Shaquille O'Neal, someone really, really big compared to Kevin Hart or some Richard Simmons, right? Someone very, very small. Not saying either one are bad. When we're looking at this, we're looking at per body surface area. We need to sort of factor in, and so that way it's more accurate. Okay, so if we would look at this, we can factor in a patient's body surface area, and that's when we would call it a Vo2 index. And this is where we take their Vo2 and divide it over their body surface area. Right, and so this is where it would be 125 to 165 mLs of oxygen per meter squared, ultimately, and that's a way to see if what's normal for that particular patient. So if I have a Richard Simmons, if I have a Shaquille O'Neal, and they're doing the metabolic test, then I can actually see if they're within normal for their size, for their body surface area. So it gives us a way more accurate than just saying 250 mLs of O2 per minute is normal for everyone. This one's going to be a way to find if it's normal for them specifically. So it's more specialized to each individual, which is great, right? Then we know if it's normal for them or if it's outside of normal for them. So if you got someone like cold Richard Simmons, and I'm not saying anything bad about Richard Simmons, but most people know who that is. If you have that person that's cold in small body surface area, they're not going to have a high oxygen consumption traditionally, right, compared to someone that has a more massive body surface area. All right, so don't worry about the Vo2 index. I put that in there. That's sort of bonus information. But when we're looking at the oxygen extraction ratio, this is another one that you do need to know. So this is just a different way of looking at Vo2 consumption, okay? Whew. Did I come up with all these? No, but I'm here to help you through all this. So a different way to look at consumption. So this is look at your extraction ratio. How much oxygen is extracted by the tissues from what's delivered. And so when you're looking at this, this is your A to V over your A. So CO2 minus CVO2 over CaO2. And your answer is going to be in volumes percent, because everything going into this is volumes percent. So your units are still going to be volumes percent. You'd be like, Derek, doesn't it cancel out mathematically? Yes, but I need to know what the number is. Like, is it 15 oranges? Is it 15 mLs? And you're like, oh no, it's 15 volumes percent, right? So just still use the units even though mathematically, right? Okay. So a healthy person usually only extracts about 25% of the available oxygen, right? Right? This is where we're looking at. So 20 minus 15 is 5. 5 over 20, so this would be 5/20 if we're looking at this one over here, right? Because I just did 20 minus 15 to get 5/20. And 5/20, when we divide it, so 20 goes into 5, 0.25. So our oxygen extraction ratio is 0.25 or 25% when we're looking at it. So this looks at a view of their transport status. So if their CO2 is low and their CVO2 is low, then we're going to have a lot more oxygen that gets extracted because there's not as much oxygen being delivered. So out of a smaller bank account, so here's a scenario. You have a bank account of $20 and every week you pull out $5. So you have a left over in your bank account $15. Next payday it goes back up to $20. Okay. Stick with me here. So the 1 week somehow something happened and your bank account only has $10 in it and you still extract or withdraw $5. So your extraction ratio that next day increased. You took out half of what your bank account was compared to what it was before. So that's sort of what you're looking at here. If your CaO2 is low and your CVO2 is low and your extraction is normal, your extraction ratio is going to be increased because you started with a lower value. So the value that this equation gives you, or the importance that this equation gives you that you don't get with the other ones, is that you can look at, compared to what I'm getting, how much am I taking? Right? Not just overall, what's my metabolic rate of my tissues, but this also looks at the metabolic, comparing the metabolic rate of my tissues to what's delivered to my tissues. So I can get a lot better information and understand that, hey, I have a 50% extraction going on. So compared to what's being delivered, I'm taking half of it. The higher that value, the more sensitive my patient's going to be to things like an increased metabolic process. The more sensitive they're going to be to a fever. The more sensitive they're going to be with a seizure desaturating. The more sensitive they're going to be desaturating to movement or anything like that. I hope that makes sense. But it's going to give us a lot more detailed information. Right? So things that can increase my extraction ratio, a lower cardiac output. We've already talked about how the cardiac output can change delivery. Anything that increases consumption, here's where you're going to see a pattern. Exercise, shivering, seizures, hyperthermia. If a patient's anemic, right, they're not carrying as much, that would decrease their CO2. Remember, there's lower hemoglobin, therefore lower CO2, therefore their DO2 is decreased, and so on. So that would increase their extraction. A decreased arterial oxygenation in the first place, so anything that decreases diffusion or perfusion. Okay, factors that decrease the extraction ratio. In other words, make it so your tissues are hardly pulling anything out of that bank account, right? Hardly withdrawing anything. Would be an increased cardiac output because we're delivering a lot more oxygen than what our tissues are consuming. Anything that decreases consumption, so paralytics, so skeletal muscle relaxers, peripheral shunting, poisons, hypothermia, all that should look familiar. Increased hemoglobin concentrations, like we see with polycythemia that happens with patients that have a chronic hypoxemia. Right, and we talked about that in the red blood cells, where with erythropoietin, how the body can compensate with chronic hypoxemia by creating more red blood cells, and that's why patients with COPD may have an increased H&H and may have polycythemia as well. Their body's trying to compensate. An increase in arterial oxygenation, therefore increases how much is in that bank account to begin with. So hopefully that bank account thing made a little bit of sense there. All right, so now I'm going to talk about something a little bit different. This isn't a calculation. Everybody take a deep breath there, right? Not a calculation. How dare he, right? This is the calculation exam. This is the fun part. In the presence of a normal saturation and normal hemoglobin levels, right, the continuous monitoring of venous oxygen saturation can detect changes in your A to V gradient, your consumption, which is the VO2, and your extraction ratio. So in other words, one of the things that we can do at the bedside, instead of calculating all these things continuously, like every 4 hours or 6 hours on a very, very sick patient, would be just to look at their venous saturations. So a normal venous saturation, SVO2, is around 75%, right? A normal oxygen consumption is 25%, or sorry, a normal O2 ER is 25%. So when we're looking at this, if we have 100% and we have a 25% consumption, our normal venous sat should be 75%, right? That's what's left over. It can get as low as 65% and still be acceptable. So that's why we sort of watch it between 65 and 75% would be your normal range, if you will. So looking at this normal range, we're going to see how much consumption has gone on, right? Their A to V gradient, their consumption, their O2 ER. So if we have a patient and here's their tissues, right? Here's their muscle and here's the blood flowing past it. And we do their venous saturations at 75%. Oh, that's great, right? And then their arterial saturation, let's just say it's 99%, right? That's great. That's doing good. But now we have the same patient. They start running a fever. Their blood pressure starts decreasing. And now we draw a venous sample. And their saturations are still good. We draw a venous sample and now they're at 55%. So that means their tissues are consuming more oxygen. And did I need to do this A to V gradient, the consumption, and the O2 ER to figure this out? No, I just drew a blood gas off of a central line and seen that their venous saturation was lower than what it was before. So we actually do this, right? This is where I give you an application point. We do this in critical care medicine. If a patient has something like sepsis, a blood infection, where the tissues have a very high metabolic rate, we actually trend venous blood gas values. And we try to look at that saturation. If that saturation is decreasing, which is what happened in this example I gave you, that means their metabolic rates increase. That means they're getting worse. If this value starts increasing again, let's say we draw it 24 hours later, which was a long time to wait to draw it again, but let's say we draw it 24 hours later, and let's say it's back up to 65%. After 24 hours, we know this patient's getting better because their tissues aren't consuming near as much oxygen. So that's sort of a way we can look at these values in critical care medicine without having to calculate your A to V gradient, your VO2, your O2 ER. So as far as critical care medicine goes, it's sort of a way that we can look at the concept of what's going on at the tissues without having to calculate all those different areas. We're just going to trend their venous saturation. So what decreases it and what increases it? Well, anything that decreases cardiac output will decrease their venous saturation, right? Because lower blood pressure means longer dwelling time. We're going to have more dwelling time for the tissues to pull oxygen out of the blood and into the tissue, so that will decrease our venous saturation, right? Anything that increases consumption, once again, you should see a pattern: exercise, seizures, shivering, hyperthermia. What would increase their venous saturation? Well, if their blood pressure increased, right, less dwelling time at the tissue level, that means there's less time for the blood to have oxygen extracted from it by the tissue, so that would increase venous saturation, or what's left over. And then, of course, anything that decreases consumption, like paralytics or shunting or poisons or hypothermia. All right, so just so you know and you're aware of, if you're out there in critical care medicine and you see us trending venous saturations, we're actually roughly looking at these three things. Is it as detailed? No, but it's something that we can look at to sort of see, okay, if our venous saturations are low, why are they low? And that's when I can move to, hey, let's figure out why they're low. I have 3 equations that can actually figure out why they're low. The O2 ER would be a great one to look at as far as looking at what's delivered versus what they're consuming. Okay. This one might take you a little while, and that is okay. This is for your benefit, okay? So this is an example problem of you calculating all of these equations. So pause it when we're done. I'll tell you when to pause. So pause it when I tell you to pause, and I want you to go through and calculate all these. And this is just like your worksheet, you practicing these calculations. You need to have these calculations down and be able to do them, know the normals, know the units. And so be able to do these, okay? So let's start at the top here. So let's check the curve. When we're looking at a CO2 and a saturation, what should our PO2 be? So when we're looking at a CO2 of 20 volumes percent, that's good, a saturation of 97%. Our PO2 should be greater than 60, right? So that makes perfect sense, right? We have a good pressure, therefore we have those good numbers. But let's say our CO2 is only 15 volumes percent. Our saturation is only 70%. Our PO2 is probably in the 45-ish range, right? If we have a normal curve. So when we're looking at this, understand that when we have these low pressures and low saturations, our ability to carry oxygen as far as volumes percent will also be decreased as well. So this is all just putting it together. Okay. Example problem. All right, so look at the bottom. There is a little typo here. Remember that cardiac output, so QT equals stroke volume times heart rate. Okay, so under here, I need you to change stroke volume to 100 mLs per minute. So that's in milliliters. Okay, so it's just a unit change there. Not a number change, just mLs instead of liters. 100 liters per minute, it's like a giraffe. Stroke volume. We're not doing this. We're doing this on a human. So 100 milliliters a minute. All right, so the first thing here, before you start calculating, right, and this is training you to be a critical thinker, before you start calculating all of these on your patient, and the board exams will do this as well. Before you start looking at that to figure out what's wrong with your patient, look at the numbers. Are these numbers within normal limits? And this is what I'm going to stress. Do you know normal? Okay. Hemoglobin's 14 grams percent. Is that normal? FiO2 is 60%. Saturation of arterial is 80%. Saturation of venous is only 60%. PO2 is only at 58 millimeters of mercury. CO2 is at 60 millimeters of mercury. PVO2 is at 30 millimeters of mercury. And our heart rate is 60 and stroke volume is 100 mLs per minute. So when you're looking at that, first of all, what things sort of stand out of normal limits? So I would label it normal, normal, not normal, right? Or high or low, right? And so before we'd ever calculate, then you might be able, just by looking at all their numbers, figure out where the issue is, right? So when we're looking at this, I want you to calculate CaO2, CVO2, capillary content, CCO2, their DO2, the delivery of oxygen, their A to V gradient, which is my favorite, just subtracting the A minus V, their VO2, as well as their O2 ER. So I want you to get all those calculations out, put the normals next to the calculation. In other words, a normal CaO2 is 20 volumes percent, normal CVO2 is 15%, normal CCO2 is 20 volumes percent, a normal DO2 is 1,000 mLs of O2 per minute, a normal A to V gradient is 5 volumes percent. So when we're looking at this, a normal VO2 is 250 mLs per minute. O2 is normal 0.25. So when we're looking at this, you can see which is normal, which is not. Is my CaO2 normal? Is my CVO2? Is my CCO2? Is my DO2, right? And then when you're looking at these, this is what you'll be doing clinically. What's outside of normal limits and what could cause it? So this is where I say go ahead and pause and then come back once you calculated all these. So now that you calculated them, I want you to look at these normal values. Now, what I'm going to do is I'm going to make sure if you guys send me the work handwritten or typed out, right, that shows me that you calculated all these and the values that you got. If you send me the CaO2, CVO2, CCO2, DO2, ADV gradient, VO2, and O2 ER, right, if you email those to me, right, ddavis@pmi.edu, if you email those to me, then I will give you credit towards this next exam, right? But these values need to be correct, right? And your work needs to be shown. So that way I can sort of see and make sure you have your units there. But I need you to do that. And then I might give you an extra point if you can tell me why this situation is happening or pinpoint what's going on with the situation. We can talk about it in the Zoom meeting, but I want you to sort of go through this and have that practice. All right, the last equation that we'll talk about here is called the shunt equation or the clinical shunt equation. So this is how much blood, so remember the definition of dead space over here. So dead space is ventilation without perfusion. Okay, so over here, the definition of a shunt is perfusion without ventilation. So there is no exchange of gas. So blood is going from the venous to the arterial side. That is not getting rid of CO2 and that is not picking up oxygen. So I want to see how much a patient is shunting. I want to see how bad their shunt is and how severe their shunt is. And anything greater than 30% is usually associated with high mortality. So we're going to look at, it's very severe, we want to act quick, we want to do some interventions to see what we can do to decrease their shunting percentage, because that means there's a lot of blood that's not exchanging oxygen, and that means their tissues could easily go into a severe hypoxemia and lead to tissue death, right? So when we're looking at this, how much blood is shunted against the total cardiac output? So this is sort of placed a little funky. So your shunt equals your CCO2 minus your CaO2 over your CCO2 minus your CVO2. It just, the dividing line just got mixed up over here. So you're taking your capillary content minus your arterial over your capillary content minus your venous. So when you divide these out, it will give you how much this patient is shunting, okay? So we need to know how much our patient is shunting because it makes a difference in how aggressive we're going to treat this patient. So when we're looking at this, right, you're going to need a lot of information. So you're going to need the barometric pressure, PO2, PVO2, hemoglobin, PBGAO2, right? So that means you're going to have to calculate the alveolar air, their FiO2, which I'll give you, their saturation, which I'll give you, venous saturation, PaCO2, right? You're going to need a lot of information, right? Because you need to calculate CCO2, CaO2, VO2, all to get their shunt equation. So anything less than 10% is considered within normal parameters. So that normal for baseline you and I is 3%, because 3 to 5%, because that's what's left over from fetal circulation. But when we're looking at clinically at the bedside, less than 10% will be considered non-significant. We're getting to 10 to 20%. There's some shunting going on, but usually we're not going to consider that clinically significant. In other words, we're not going to take a lot of action towards it, but we're going to monitor it. At 20 to 30%, this is considered significant shunting, so we should probably figure out what's going on here. If it's over 30%, we're going to take immediate action because this is a very severe condition for the patient. So when we're looking at this, you just need to be ready to do this shunt equation ultimately as well. So let's talk about the concept of the shunt equation. Well, we already talked a little bit about the concept. It was looking at out of the amount of blood that's flowing through the capillaries, how much of that did not exchange oxygen and CO2? How much of it did not participate in that gas exchange? Well, that's great. But here's the thing that we got to consider when we're looking at the shunting percentage. It's not reliable. It is not reliable with patients that have poor perfusion status. In other words, if their heart is not squeezing the blood very well, if they're hypotensive, their blood pressure is really low, or their blood vessels are very dilated, like a sepsis type situation, then that's probably what's causing our oxygen issues. It's because the heart's not delivering it. We have a decreased cardiac output. We have a poor vascular activity, and so that's going to be the big issue. So the patient has poor hemodynamics. Well, the shunt equation is not going to be very helpful to us. So that includes their myocardial output, their cardiac output. So that's why we need to look at their pulse pressure, which is the difference between their systolic and diastolic. And the pulse pressure, the difference between systolic and diastolic pulse pressure, is a way to look at stroke volume, right? And then heart rate. Remember, stroke volume and heart rate equals cardiac output. So I can stand at the bedside and understand what's happening to their patient's cardiac output as I make changes on the ventilator, right? Because I can see what's happening with their pulse pressure and their heart rate live. All right. So if their pulse pressure is pretty narrow, that means their stroke volume is very low. So let's say if it's 90/80, that's a very low stroke volume, right? So that's not going to equate to a good cardiac output, and therefore that might be why my patient has such a poor time getting oxygen delivered to their tissues, right? Unstable consumption demand. This can happen especially with burn victims where they burn off layers of tissue. Their metabolic rate can be high, their metabolic rate can be low. There's a lot of variables in there. So the shunt equation is not reliable with a perfusion, cardiac status, or unstable oxygen demand, especially if they're going on paralytics and off of paralytics, or a burn victim. Things like that can all factor in here. So those are types of patients we're not going to look at the shunt equation as much on, because those are all factors that we know can change someone's oxygen demands. So in medicine, a shunt is something that we actually use. You can actually have a shunt. People that build up a lot of cerebrospinal fluid can get a shunt placed in where excess fluid from their head will drain into their abdomen somewhere, and their body just reabsorbs it, right? In medicine, a shunt is a small passageway that allows it from one part of the body to another. So this can be natural or unnatural. And so this is where you're going to see in your chapter where it talks about anatomic shunts or true shunts versus a shunt-like effect. And I do expect you to go through this in detail. I do expect you to do this in your workbook. And I do expect you to have shunt versus shunt-like, true shunt versus shunt-like effects down as to what is in which category for the exam. Yes. So in medicine, we can do this. It can be a naturally occurring one. One is called a fistula or an AV malformation. So these are little things where you can get arterial and a venous that sort of fuse together, right? And that's where you have good blood and bad blood mixing together, and there's no exchange of gas. They just mix together, and therefore it decreases the amount of oxygen altogether. That would be an example of an anatomic shunt. So what are other examples of anatomic shunts? Well, this can include your bronchial, pleural, and Thebesian veins, right? Those are the ones that we've already talked about. This can include like a congenital heart disease. This can include the fistulas that you're seeing here, right, where you have the arterial and venous, or even a lung tumor, right? A vascular lung tumor can easily cause a true shunt. So how do I know if it's a true shunt? Right. So how do I know if it's a true or an absolute shunt? It means it's going to be what's called refractory to oxygen therapy. That means in this situation, right, where I have this like tumor that's forming in my lungs. Okay, let's just say it's a tumor. Or it can be a fistula. It's forming in the lungs. If I give this patient a lot of FiO2, a ton of FiO2, will it change this area? Will it change that area and improve gas exchange to that area? No, because it's a direct connection in between arterial and vein. It's not going to change that patient's shunting percentage. It's not going to change the oxygen level in their bloodstream. So a capillary shunt is a true shunt. It's an absolute shunt, right? It's refractory to oxygen therapy. In other words, I put this patient as much oxygen as I can, and because this does not have anything to do with the alveoli, it's not going to change their saturation. It's not going to change their PaO2. Right? It's not going to change it. So if I put a patient on a lot of oxygen and it doesn't change their saturations and PO2s much at all, then that is a true or anatomic or absolute shunt. So vascular lung tumors, capillary shunts, which can include atelectasis, fluid accumulation, alveolar consolidation. Those are all capillary shunts, and they can act like absolute shunts where you can put these patients on oxygen. It's not going to change much. So in the case of atelectasis, where your alveoli is all shriveled up, you can give as much FiO2 as you want here, but you may not have a change in the oxygen levels at all because your surface area is so small that they may be refractory to all that extra oxygen you're giving them. So these are capillary or true or absolute shunts. So that things like atelectasis act like a true shunt, but it's not. It's reversible. When we have the situation, we can reverse it. We can get the patient's lungs to open up a little bit more. But when we're looking at this is something that we need to have a deeper understanding of when our patient's not responding to oxygen. That's more of a true or absolute shunt. And so one of the things that we have to look out for is something called a shunt-like effect. So shunt-like effect means it's going to have the ability where we have the alveolar capillary relationship, but this is something where they will respond to oxygen therapy. So what are some causes of a shunt-like effect? Well, hypoventilation would be a shunt-like effect. So this would be a low CO2 level, right? Hypoventilation. This would be a high CO2. So high CO2. So that would be a shunt-like effect because there's all that CO2 built up in the bloodstream and in the alveoli itself because they're not breathing, right? Think about someone that took a little too much of their pain medicine and are hypoventilating, right? So that would be a shunt-like effect. In this patient, if we get them to breathe more and get rid of that CO2, according to Dalton's law, we get rid of that CO2 in the alveoli, we'll get rid of CO2 in the bloodstream, and therefore they'll be reactive to change, unlike a patient that has a true or absolute shunt. Right? So hypoventilation is going to be one of them. A VQ ratio, bronchospasm, mucus accumulation, a diffusion defect like we see with people with emphysema. We talked about that with a thick AC membrane or destroyed AC membrane like pulmonary fibrosis and emphysema. Those are all things that are going to be shunt-like effects. but they will respond to oxygen therapy, right? They're readily corrected by oxygen therapy. So a true shunt or anatomic shunt or absolute shunt, all of those three will not respond well to oxygen therapy, but a shunt-like effect will respond well to oxygen therapy. So go over those, make sure you know those. Make sure you got those down. A true shunt-like effect. Make sure you know the difference in what could be in the true shunt versus a shunt-like effect category, and then your workbook should have practice on those as well. So pulmonary shunting is a part of the cardiac output that moves from the right side of the heart to the left without being exposed to alveolar oxygen. So this is an occasion where you actually see with the pulmonary shunt, these are more of your true shunts, right? So you can put this patient on as much oxygen as you want to, but if it's bypassing everything altogether, you're not going to see, right? An anatomic shunt, you can put this patient on as much FiO2 as you want, it's not going to change this bypass that your body created, right? Capillary shunts, and this is where I was talking about how these are true shunts. You can see how this is an issue where the capillary is not even in contact with the alveoli. It's not in communication with it anymore. And therefore it acts like a true shunt because there's no communication. There's no ability to exchange gas. So if I give this patient a ton of FiO2, they will not respond, right? If I give this patient with anatomic, they will not respond. If I give this patient with a shunt-like effect, right, there's something like an obstruction going on or a thickened AC membrane, this patient may have an effect, right? This is where I increase the FiO2 on this patient, and it may increase their saturations and PO2s. Okay, so if it's a shunt-like effect, then they'll respond to increased FiO2. If it's a true shunt or anatomic or capillary, they will not. So if you're at the bedside, a patient comes in, their oxygen levels are low, and you put them on a ton of oxygen, right? And their oxygen levels start to come up, you know it was a shunt-like effect. If you put them on a ton of oxygen and their saturations and their PO2s don't change at all, then you know it was probably an anatomic capillary true shunt situation. Okay, so this is just a different way of looking at it. If you're a flowchart person, hopefully this helps. If you're not a flowchart person, this does not exist to you. So a cardiopulmonary shunt, it can either be a shunt-like effect or an absolute true shunt. That's why we see those branches here. If we're looking at an absolute true shunt, that can be an anatomic shunt, which is where you're born with a congenital heart defect, or you have a fistula that developed, or you have a tumor that developed. That means their body will not respond to FiO2. So, not respond to FiO2. Right? What about over here with capillary shunts? Alveolar collapse, atelectasis, consolidation, accumulation. If this is going on, they will also not respond to FiO2. However, can these be reversed? Can I reverse alveolar atelectasis? Yes, I can give them more pressure. If they're a premature baby, I can give them surfactant, right? If they have consolidation, we can do things like diuretics, things like that. So those are all things that we can do, but in the initial phase, they will not respond to FiO2. So these are true and capillary shunts. They do not respond to FiO2. And over here, this category, and I'll use yellow, they will respond to oxygen. Okay, so if I give them high FiO2s, if I have a patient that is hypoventilating and I put them on a lot of oxygen, if I have a patient that has something like COPD or a lot of secretions or a diffusion defect like pulmonary fibrosis, if I put them on oxygen, if I use a high FiO2 on them, their saturations, their PO2s, they should all start to come up, right? They should respond to that. So that is just one way of knowing if a patient's oxygen levels are secondary to a true shunt or to a shunt-like effect. So if you put them on oxygen, their saturations start coming up, their pressure of oxygen in their bloodstream comes up, then you know it was a shunt-like effect. And then you know to look at things like hypoventilation, a VQ mismatch, or diffusion defect. If they don't come up, right, if their PO2s and their saturations don't come up, then I can look at something like atelectasis, consolidation, which is something that can go on with heart failure, things like that. And then you can start narrowing down what's causing this patient's issue. So not only are you being therapeutic, but you're also being diagnostic at the same time.